What if the most profound secrets of our universe were not hidden in distant galaxies or beneath ancient oceans, but woven into the very fabric of existence at its smallest scales? Imagine two particles separated by light years, perhaps even created at the dawn of time, yet sharing a destiny so intertwined that a change to one instantly affects the other. This isn't a theoretical curiosity, a mere quirk of mathematics. It is a fundamental, baffling reality. A connection so immediate, so complete, that it appears to defy everything we thought we understood about space-time and the speed limit of light. Even the brilliant mind of Albert Einstein wrestled with its implications, famously calling it spooky action at a distance. It paints a picture of a universe far stranger, far more interconnected than our everyday experience suggests. It forces us to question the very nature of what is real, what is separate, and what it truly means to be. How can this invisible, instantaneous thread bind together the most distant corners of our cosmos? The cosmos, in its grand and infinite expanse, holds mysteries that defy our most fundamental understanding. Among them, one phenomenon stands out as particularly perplexing: quantum entanglement. It proposes an invisible, undeniable link between two or more particles, so intimate that they behave not as separate entities, but as two halves of a single unified system, no matter the vast distances separating them. Picture this one particle here in your hand, its twin soaring through the void, perhaps light years away. A measurement performed on your particle, influencing its distant counterpart instantaneously faster than light could ever travel. This isn't theoretical speculation, nor the stuff of science fiction. It is a demonstrable, mind-bending reality. This inexplicable interconnectedness shatters our classical intuition, which dictates that interactions require a medium, a force and time, to traverse space. In our familiar world, a distant event cannot influence a local one without a signal traveling between them. Yet the quantum realm seems to operate by a different set of rules entirely. Entanglement introduces a direct, immediate correlation, challenging deeply ingrained notions of locality and independent existence. It speaks to a universe where the fabric of reality is far more intricately woven than we could have ever conceived. For generations, this spooky action at a distance, a term coined by one of physics' greatest minds, remained a profound theoretical paradox. It was a prediction of quantum mechanics that seemed too bizarre to accept, prompting intense debate about the completeness of our scientific models. It compelled physicists to question whether our understanding of the universe was fundamentally flawed. Yet, through decades of meticulous experimentation, pushing the very boundaries of our technological capabilities, entanglement has transitioned from a perplexing hypothesis to an undeniable verified truth. Its confirmation has not only solidified the foundations of quantum theory, but has unlocked entirely new vistas for scientific inquiry and technological innovation, forever reshaping our perception of the universe's most hidden mechanisms. To truly embark on this journey into the quantum world, we must set aside these ingrained classical assumptions and open our minds to a universe that operates with an extraordinary and utterly compelling logic of its own. For centuries, our comprehension of the cosmos found solace in the tenets of classical physics. This framework presented a beautifully deterministic universe, a grand clockwork mechanism where every component moved with predictable precision. Within this familiar paradigm, interactions are straightforward, governed by direct contact and proximity. The collision of billiard balls, the gravitational pull of planets, the propagation of light across galaxies, all occur with a defined speed bound by the universe's ultimate velocity limit. These are the intuitive principles that shape our daily perceptions, forming the bedrock of common-sense reality. In this classical domain, everything possesses clear, independent properties. A spinning top, unobserved, still maintains a definite rotational speed. A ball launched into the air follows a predictable arc, its trajectory precisely determined by initial forces. Here, every effect stems from a local cause, traceable through a chain of contiguous interactions. This profound intellectual edifice, meticulously constructed by minds like Newton and Einstein, has offered an unparalleled explanation for the cosmos at the macroscopic scales we inhabit. It has allowed us to chart the intricate dance of planets and engineer the marvels that define our civilization. It is by all measures a triumph of human reason, seemingly complete, logically consistent, and reassuringly predictable. Yet as we plunge into the subatomic realm, into the bewildering depths of quantum mechanics, these comforting classical certainties begin to unravel. The very axioms governing our macroscopic experience no longer hold. Particles cease to behave like predictable miniature billiard balls. Instead, they exist in a state of elusive potential, their properties undefined until the act of measurement itself. And here, we encounter entanglement, a phenomenon that fundamentally contradicts the bedrock principles of classical physics. It unveils correlations that defy the need for physical intermediaries, or signals an apparent instantaneous connection that transcends any known speed limit. This radical departure from the familiar is precisely what makes entanglement so revolutionary. It operates beyond the established strictures of locality and deterministic properties, pushing against the very boundaries of our common understanding. This is not merely a subtle adjustment to an existing scientific framework. It represents a profound re-evaluation of reality at its most foundational level. It leaves us with a compelling question. If the very foundational rules break down at this quantum scale, what deeper, more intricate reality still awaits our comprehension? In this subatomic theater, fundamental particles defy simple visualization. They don't exist as definitive points, but as clouds of probability capable of occupying multiple states concurrently until the moment of observation. An electron, for instance, might appear here one instant and there the next, without seemingly traversing the intervening space. Its inherent characteristics, such as spin or energy, are not predetermined values awaiting discovery, but rather a spectrum of potentials only crystallizing into a single definite outcome when measured. This fundamental unpredictability is a hallmark of the quantum world. Deterministic certainty yields to a statistical reality where we speak not of absolutes, but of likelihoods. We cannot, for example, simultaneously know a particle's exact position and its precise momentum with perfect accuracy. Instead, our understanding operates on probabilities calculating the chances of a particle exhibiting one behavior over another. It is a domain where the act of observation itself becomes an active participant in shaping what is real, a concept that profoundly challenged the greatest scientific minds of the 20th century. Consider light, for instance. For centuries, it was understood purely as a wave, a model that elegantly explained its behavior, including phenomena like diffraction and interference. Then, in a pivotal shift at the dawn of the 20th century, groundbreaking work by Max Planck and Albert Einstein revealed that light also behaves as discrete packets of energy, now known as photons. These tiny particles of light underpin effects, like the photoelectric phenomenon, where light energy is absorbed in distinct quanta. So light simultaneously manifests as both a wave and a particle, a wave of probability that coalesces into a particle when detected. This radical notion defied classical intuition, yet it became a verified truth of the universe. The quantum strangeness, however, extends beyond light. What if the reverse were also true? Could matter itself, the very building blocks of our seemingly solid reality, like electrons, protons, and even entire atoms, exhibit wave-like characteristics? This audacious hypothesis, put forth by Louis de Broglie, posited that every particle has an associated wavelength. Later experiments, notably the diffraction of electrons through crystal lattices, stunningly confirmed this. Electrons, conventionally seen as discrete particles, produced interference patterns, a signature trait of waves, not solid objects. This doesn't imply an electron literally ripples through space like a water wave. Instead, the wave describing a quantum particle is a probability amplitude. It defines the likelihood of finding the particle at a particular location or in a specific state. Prior to any observation, the particle exists as a diffuse wave of potential spread across possibilities. It is only through interaction, through the act of measurement, that this probability wave collapses, forcing the particle to manifest as a single definite entity with concrete properties at a precise point. This wave-particle duality is not a mere scientific curiosity. It forms a foundational pillar of quantum mechanics absolutely vital for grasping the inherently probabilistic nature of the quantum realm. It explains why quantum entities lack fixed positions or definite properties until observed. This inherent fuzziness, this blurring of classical lines between distinct forms of existence, is what prepares us for even more astonishing phenomena, such as superposition, and ultimately the profound interconnected reality of quantum entanglement. It reveals the very essence of what makes the quantum world so alien, so incredibly powerful, and so rich with untapped potential. Having embraced the wave-like essence of particles and the probabilistic nature of the quantum stage, we now confront a profound, inescapable truth that redefines the limits of knowledge itself, the Heisenberg uncertainty principle. In our macroscopic world, we operate under the comforting assumption that with sufficient precision and the right tools, we can pinpoint every detail about an object. We can, for instance, simultaneously determine a car's exact location and its precise velocity. This is a bedrock tenet of classical physics. Every property in theory can be known with infinite accuracy, yet at the quantum scale, this intuitive certainty vanishes. Werner Heisenberg's groundbreaking principle reveals an inherent fundamental boundary to what we can simultaneously know about a particle. It dictates that certain pairs of complementary properties, known as conjugate variables, cannot be measured with perfect precision at the same time. The more accurately one property is known, the less accurately its counterpart can be ascertained. The most illustrative example involves a particle's position and its momentum, a measure of its mass and velocity. Attempting to precisely locate an electron inevitably perturbs its momentum in an unpredictable fashion. Conversely, if we endeavor to fix its exact momentum, its position becomes inherently vague, a diffuse smear across space. This is not a deficiency in our instrumentation, nor a mere limitation of current technology. It is a profound characteristic woven into the very fabric of quantum reality. There is no hidden pre-existing certainty waiting to be unveiled. The particle simply does not possess both precise properties simultaneously until compelled into a definite state by observation. This intrinsic indeterminacy doesn't arise solely from the act of measurement disturbing the system, though that interaction is part of it. It's rooted deeper in the wave-like nature of quantum particles. If a particle's probabilistic wave is broadly distributed, indicating a clear, precise momentum, its spatial location will be highly uncertain. Conversely, if its wave is sharply concentrated in space, pinpointing its position, its momentum will be correspondingly indistinct. It's a fundamental trade-off, an irreducible blurring at the heart of existence. This unavoidable embrace of uncertainty marks a radical departure from the deterministic universe of classical physics. It underscores that the quantum realm is inherently probabilistic, a domain where outcomes are fundamentally governed by likelihoods rather than absolute certainties. This intrinsic quantum indeterminacy This inability to define all aspects of a particle's existence simultaneously lays the crucial groundwork for even more astonishing quantum phenomena. It is an indispensable conceptual leap that prepares us for the extraordinary characteristics of superposition, and most compellingly, the deep interconnectedness of quantum entanglement. Having grappled with the inherent uncertainty that defines the quantum world, we now pivot to another of its most astonishing principles, superposition. In our familiar macroscopic reality, an object occupies a single definite state at any given moment. A flipped coin mid-air is either heads or tails, even if we don't yet know the outcome. A light switch is definitively on or off. There's no ambiguity. Its state is fixed. But at the quantum scale, particles defy this singular existence. Superposition describes a quantum particle's remarkable capacity to exist in multiple states simultaneously. Imagine that coin again, but this time it is literally both heads and tails at once before it ever lands. It's not merely a state of unknown outcome. It is the physical embodiment of all its potential realities concurrently. An electron can spin both clockwise and counterclockwise, or be present in several locations at once, or possess a blend of different energy levels all at the very same time. It's a hazy, probabilistic blend of all its possible outcomes, a wave of pure potential, rather than a singular concrete reality. This enigmatic state of being and not being is not a limitation of our observational tools. It is the particle's fundamental reality until it is subjected to an external interaction. The particle's quantum state, mathematically described by its wave function, encapsulates all these probabilities simultaneously. It's like a symphony, where every note of a chord is sounding at once, rather than a sequence of individual tones. This multifaceted existence persists as long as the particle remains isolated and undisturbed by its environment. The implications of superposition are profound. This principle lies at the core of why quantum mechanics is so powerful, diverging so dramatically from classical physics. It means that quantum systems can encode vastly more information and offer significantly greater computational potential than their classical counterparts. While a traditional computer bit must be either a 0 or a 1, a quantum bit, or qubit leverages superposition to be both 0 and 1 simultaneously. This inherent capacity for multiple states exponentially expands the possibilities for information processing. Crucially, the instant we attempt to observe or measure a quantum particle in superposition, this delicate state collapses. The wave of possibilities instantly resolves into a single definite outcome. That quantum coin, once a blend of heads and tails, instantaneously becomes either one or the other upon inspection. The electron spread across multiple locations chooses a specific position when measured. This abrupt transition from a probabilistic blend to a concrete reality is known as wave function collapse, and it remains one of the most central and still partially mysterious aspects of quantum mechanics. Understanding superposition is absolutely vital, as it is this strange ability that enables quantum particles to become intricately linked in the phenomenon we call entanglement. We have now delved into the bewildering wave-particle duality, observed how matter and energy exist as fluid probabilities rather than fixed certainties. We've grappled with the Heisenberg uncertainty principle, revealing the fundamental limits to precisely knowing a particle's properties, a profound intrinsic fuzziness within reality itself. And we've explored superposition, the astonishing capacity for quantum entities to simultaneously inhabit multiple states, a blend of all possibilities, until an interaction forces a singular outcome. Individually, each of these concepts challenges our deepest intuitions. Collectively, they interweave to form the strange, vibrant tapestry of the quantum world, a realm fundamentally unlike our macroscopic experience. Consider, if you will, our classical universe as a meticulously rendered painting, where every detail is sharp, every color definitive, every object precisely placed. The quantum universe, by striking contrast, resembles an impressionist masterpiece, a vibrant collection of brush strokes, each representing a possibility, coalescing into a shimmering cloud of potential. Only when we choose to focus on a particular point to measure it does a specific detail emerge from this blur, solidifying into a definite form. This is the very essence of quantum reality, a landscape where the fundamental constituents of the cosmos do not possess fixed attributes until they are observed or interact with their environment. At these infinitesimal scales, certainty as we know it proves largely illusory. Instead, the universe unfolds as a dynamic interplay of probabilities, and our role as observers is far more consequential than classical physics ever hinted. An electron, for instance, isn't simply at a fixed location. It exists as a probability distribution, a potential to be found across various points, each with a specific likelihood. Its intrinsic spin isn't definitively up or down, but a superposition of both orientations. It is only the act of measurement that compels this wave of possibilities to collapse, actualizing one of the potential outcomes. This renders the quantum world intrinsically probabilistic, a domain where definitive outcomes are not predetermined, but rather emerge from a sophisticated dance of chance, meticulously governed by the precise mathematical laws of quantum mechanics. This intricate web of wave-particle duality, inherent uncertainty, and the astonishing power of superposition defines the true, perplexing essence of the quantum realm. This is a universe where particles are not isolated miniature versions of the objects we encounter daily, but rather complex, context-dependent manifestations of a deeper, more fluid reality. Grasping this peculiar framework is far more than a mere academic exercise. It is the crucial gateway to understanding one of the universe's most profound and revolutionary secrets: how these very principles allow particles to become inextricably linked, forever bound, by an invisible thread in the phenomenon known as quantum entanglement. Having established the peculiar landscape of wave-particle duality, intrinsic uncertainty, and the astonishing phenomenon of superposition, we now arrive at the core of our exploration: quantum entanglement. This fundamental concept describes an extraordinary, unbreakable link forged between two or more particles. Once entangled, their individual quantum states become irrevocably intertwined, meaning they no longer exist independently. Instead, they form a single unified quantum system, sharing an inherent connection, regardless of the immense distances that might separate them across the cosmos. Consider for a moment two photons created simultaneously, each carrying a specific polarization, a direction of oscillation. Before observation, neither photon has a definite polarization. Each exists in a superposition of both vertical and horizontal. Now imagine sending one of these entangled photons to a distant laboratory on Mars, while the other remains here on Earth. The instant a scientist on Mars measures their photon and finds it to be, say, vertically polarized, the photon on Earth at that very same moment instantaneously resolves from its superposition and definitively becomes horizontally polarized. This remarkable correlation is not the result of a hidden variable or a secret signal. It is a direct, immediate consequence of their shared, entangled state. This profound interconnectedness is the defining characteristic of entanglement. The particle's properties, be it spin polarization or energy level, become perfectly correlated. When a measurement is performed on one entangled particle, forcing its quantum state to resolve from its probabilistic superposition into a definite outcome. Its entangled partner, no matter how far away, simultaneously collapses into its complementary definite state. The outcome of the first measurement dictates the outcome of the second with absolute certainty, bypassing any need for information to travel between them. It is this non-local instantaneous correlation that both captivated and confounded the founders of quantum mechanics. In the classical universe, no influence can propagate faster than the speed of light. Yet entanglement implies a direct correspondence, a cosmic dance where partners always know each other's moves, seemingly transcending the conventional barriers of space. It's as if these separated particles remain part of one extended quantum whole, their individual identities subsumed into a collective state until observation compels them into specific complementary realities. This then is quantum entanglement, a phenomenon where the quantum properties of distinct particles are so deeply interdependent they cannot be described in isolation. It reveals a universe at its most fundamental level that is far more interconnected than our classical intuitions can readily grasp. This astonishing non-local bond not only underpins some of the most profound scientific debates of the past century, but also forms the crucial foundation for the next generation of revolutionary technologies. The most striking and indeed the most deeply perplexing attribute of quantum entanglement is its seemingly unmediated connection. We've established that once particles become entangled, their quantum states are inextricably bound. But the true astonishment emerges the moment one of these particles undergoes a measurement. Consider our photon on Earth intrinsically linked to its counterpart, hurtling towards Mars. The instant the Martian photon is measured, perhaps yielding a vertical polarization, the Earth-bound photon immediately, and without any discernible delay, collapses into its complementary horizontal polarization. This perfect correlation manifests regardless of the immense cosmic void separating them. This immediate simultaneous determination of states challenged the very foundations of physics for its pioneers. Our classical understanding of the universe, rigorously defined by Einstein's theories of relativity, posits an absolute cosmic speed limit. Nothing can transmit information or influence faster than light. Forces signals all forms of interaction must propagate through space at or below this universal maximum. Yet entanglement presents a direct defiance of this bedrock constraint. There appears to be no signal, no exchange of energy, no intermediate force traveling between the entangled particles. Their specific properties simply become known with perfect synchronicity across unimaginable distances. It was precisely this baffling aspect that compelled Albert Einstein to famously brand entanglement as spooky action at a distance. He, alongside his esteemed colleagues Boris Podolsky and Nathan Rosen, found this non-local correlation profoundly unsettling. They argued it implied either a fundamental incompleteness in quantum mechanics or a violation of locality, the principle that an object can only be influenced by its immediate surroundings or by interactions traveling to it at a finite speed. How could the act of observing one particle instantaneously dictate the reality of another light-years away, without any classical means of communication? This stark paradox, the notion that a measurement on one particle instantaneously fixes the state of another across vast cosmic gulfs, raised the specter of faster-than-light communication, a concept anathema to relativity. It forced physicists to question whether reality itself was truly local. This apparent contravention of our most cherished physical laws ignited one of the most intense and enduring debates in the annals of science, pushing the boundaries of what was considered possible within the fabric of space-time and causality. The seemingly instantaneous bond between entangled partners remains a powerful testament to the truly counterintuitive nature of the quantum realm, compelling us to redefine our understanding of connection itself. To truly grasp the profound implications of entanglement, let us delve into a concrete illustration of these intrinsically linked quantum systems. Consider two electrons precisely generated such that their spins are entangled. Spin in the quantum mechanical sense is a fundamental intrinsic angular momentum, much like a tiny magnet's orientation, which can be measured as either up or down along a given axis. Crucially, until observed, each electron exists in a superposition simultaneously embodying both up and down spin states. They possess no definite spin direction in isolation. Now picture these two entangled electrons. One, let us designate it, electron A, remains with an observer here on Earth. Its partner, electron B, embarks on a journey traveling millions of miles to a distant space station orbiting Jupiter. According to the principles of superposition, neither electron A nor electron B has a fixed spin direction. Both exist in a hazy probabilistic blend of up and down. Yet here is where the astonishing reality of entanglement dramatically asserts itself. Their fundamental properties are inextricably linked. The observer on Earth decides to measure the spin of electron A. The very instant this measurement is performed, electron A's superposition collapses, and its spin definitively resolves, for instance, to up. At that precise, unmeasurable moment, electron B, separated by light minutes near Jupiter, simultaneously resolves from its own superposition and unequivocally takes on the complementary spin down. This occurs without any discernible signal traversing the immense cosmic chasm between them. No known force or communication mechanism bridges the vast distance. Their individual quantum realities, once uncertain, become fixed in perfect opposition, as if they were always part of a single extended entity. This is the essence of their interwoven nature. A measurement on one particle instantaneously determines the corresponding property of its entangled partner, irrespective of their separation. It's not a case of the electrons possessing predetermined spins that we simply didn't know that would align with classical notions of hidden variables. The true quantum marvel lies in the fact that their properties were genuinely indefinite until the act of observation, yet their outcomes are perfectly non-locally correlated. One simply knows what the other is at the very same instant. This remarkable correlation, where the act of resolving one particle's superposition compels a complementary resolution in its distant partner, underscores the radical departure of quantum mechanics from our everyday experience. Their properties are not merely intertwined, they form a singular quantum state stretched across space. This fundamental interconnectedness defies our classical intuition, profoundly pushing the boundaries of what we consider possible for objects separated by vast distances. It unveils a universe operating on principles far more intricate and far more deeply connected than our macroscopic world could ever suggest. Having explored the astonishing reality of instantaneous correlation, where a measurement on one entangled particle immediately shapes its distant partner, we are compelled to view this phenomenon through a new lens. It represents a connection that fundamentally transcends our conventional understanding of space and time, as if the particles are not truly separate entities, but enduring components of an indivisible whole. This profound interconnectedness is perhaps best illuminated as a grand cosmic dance, a precisely choreographed ballet unfolding on the universe's most expansive stage. Imagine two dancers' partners intricately linked in a complex performance. They begin their routine in perfect unison, their every movement a mirror of the other. Then they gracefully separate, each gliding to opposite ends of an immense hall beyond any visual or auditory contact. Yet the precise moment one dancer executes a specific turn or extends an arm, the other far across the expanse simultaneously performs the exact complementary step with flawless harmony. There is no visible cue, no whispered instruction, no time delay for information to pass between them. Their actions are simply intrinsically correlated, as if guided by an unseen shared score that binds their every gesture. This illustrates the elegant yet deeply enigmatic choreography of entangled particles. Their intrinsic properties, such as spin or polarization, do not exist in a fixed state prior to any observation. Instead, they reside in a fluid superposition of possibilities. But the instant one particle is measured, its potential crystallizes into a definite reality, and its entangled partner, irrespective of the cosmic gulf, instantly resolves into its complementary state. It is a unified, synchronized response, a profound reflection of their shared quantum identity. This vivid metaphor extends beyond mere analogy. It captures the astonishing beauty and inherent marvel of entanglement. It suggests a universe where its most fundamental components are not isolated units, but rather active participants in a continuous interlinked performance. Their shared quantum state guarantees that their individual moves are always precisely coordinated, whether they are mere millimeters apart or separated by light years. This seamless coordination hints at a deeper underlying unity, a universal rhythm that effortlessly bypasses the classical constraints of space and communication. This intricate, synchronized cosmic dance directly challenges our ingrained notions of independence and locality. It unveils that at the very core of existence, there lies a profound fundamental bond that weaves particles together in a manner that remains deeply perplexing, yet undeniably magnificent. It reinforces the compelling idea that the universe at its most elementary level might be far more profoundly interconnected than our macroscopic perceptions can fully grasp. The extraordinary, seemingly instantaneous connection between entangled particles inevitably sparks a compelling question. Could this phenomenon offer a pathway to send messages faster than the speed of light, effectively shattering Einstein's most fundamental cosmic speed limit? This is a vital point to clarify, and the definitive answer is no. For all its perplexing non-locality, quantum entanglement cannot be leveraged to transmit information at superluminal speeds. The reason lies in a crucial aspect of quantum mechanics, the inherent randomness of measurement outcomes. When you observe an entangled particle, say, measuring the spin of electron A on Earth, the result, whether up or down, is fundamentally probabilistic. You, as the observer, cannot predetermine or force a specific outcome to encode a 1 or a 0. The particle's superposition ensures that its collapse into a definite state is entirely random from your perspective. Therefore, you possess no control over the message that is seemingly sent. Even though electron B on a distant planet will instantly adopt the complementary spin to electron A, the observer on that distant world has no prior knowledge of what state their particle will assume until they perform their own measurement. And once they measure it, they are left with a random outcome. Their electron is simply up or down. They cannot discern whether this state was caused by a measurement on Earth, or if it was merely a random collapse from their own superposition. To confirm the correlation, to verify that their down indeed matches an up on Earth, the two observers must compare their results. This comparison critically must occur via conventional communication channels, like radio waves or laser pulses, which are by definition bound by the speed of light. Thus, while entanglement beautifully demonstrates a profound non-local correlation, an undeniable instantaneous linkage, it does not enable faster-than-light communication. No usable information can be extracted or sent without resorting to classical communication, which adheres strictly to the cosmic speed limit. This crucial distinction ensures that quantum mechanics, despite its myriad strangeness, remains entirely consistent with Albert Einstein's theory of special relativity and its bedrock principle that no information or causal influence can ever propagate through the universe faster than the speed of light. This elegant reconciliation, though it once formed the basis of profound scientific disagreement, only deepens the wonder of the quantum realm. Having explored the astonishing reality of entanglement and the crucial understanding that it cannot transmit information faster than light, we now turn to the profound intellectual turmoil this phenomenon ignited. Despite its elegant mathematical framework, entanglement presented a deep paradox, a fundamental assault on the very foundations of scientific understanding, meticulously constructed over centuries. It was far more than a mere curiosity. It was a conceptual earthquake shaking the pillars of classical physics and deeply troubling the greatest minds of the 20th century. The central conflict stemmed from entanglement's apparent violation of two cherished classical tenets: locality and realism. Locality asserts that an object can only be directly influenced by its immediate surroundings or by interactions traveling to it at a finite speed. Entanglement, with its instantaneous correlations across vast distances, seemed to tear this principle asunder. Realism, meanwhile, posits that physical properties exist independently, possessing definite values whether observed or not. A particle has a precise spin, whether we measure it or not. But quantum mechanics, with its wave functions and superposition, implied these properties only become definite upon measurement. Entanglement pushed this even further, suggesting that observing one particle could instantly define the reality of another far-off particle, thus challenging the very notion of a locally real universe. This ideological clash between the seemingly non-local probabilistic nature of quantum mechanics and the local deterministic cosmos of classical physics became the crucible for one of science's most intense philosophical battles. To many, particularly those steeped in the elegant certainty of classical thought, quantum mechanics, especially with entanglement at its heart, felt inherently incomplete. It painted a picture of a universe intrinsically uncertain, where the act of observation played a bizarre active role in shaping reality, and where distant connections defied all rational intuition. How could such an undeniably successful theory contain an element so fundamentally at odds with common sense and with Einstein's meticulously verified principles of relativity? This was the intellectual gauntlet thrown down by entanglement. Was quantum mechanics merely a provisional, albeit highly effective description of a deeper, more rational reality yet to be uncovered? Or did it unveil a truth about the universe so alien that it demanded a complete re-evaluation of what we considered real and knowable? This unresolved tension fueled decades of fervent debate, setting the stage for a series of ingenious experiments designed to definitively settle this profound scientific mystery, compelling physicists not just to describe the universe but to redefine truth within its baffling depths. The conceptual earthquake ignited by quantum entanglement, unsettling the very foundations of scientific understanding, traces its unexpected origins to a seemingly intractable problem at the close of the 19th century. Classical physics, despite its impressive predictive power, found itself utterly baffled by the behavior of black body radiation, the way objects emit light when heated. Existing theories erroneously predicted an infinite output of ultraviolet light, a catastrophic absurdity infamously dubbed the ultraviolet catastrophe. It was into this perplexing crisis that Max Planck, a German theoretical physicist, stepped inadvertently, setting the stage for a revolution. In 1900, Planck put forth a radical, almost reluctant hypothesis. He proposed that energy was not emitted or absorbed in a continuous, smooth flow, as prevailing classical theories assumed, but instead in discrete, indivisible bundles, which he termed quanta. To illustrate, imagine energy not as a fluid flowing down a ramp, but as distinct steps on a staircase. Energy could only be transferred in these fixed quantized increments. This was a profound departure from established thought. Planck himself initially viewed this notion more as a mathematical expediency, a computational artifice to align his equations with observed data, rather than a deep insight into the intrinsic nature of reality. Nevertheless, this deceptively simple, audacious proposal fundamentally transformed the scientific landscape. It introduced the groundbreaking idea that energy at its most fundamental level arrives in irreducible units, breaking definitively from the concept of continuous streams. This quantization of energy served as the unexpected genesis of what would become the formidable field of quantum mechanics. It marked the precise moment when the universe at its smallest scales began to reveal itself as operating under rules profoundly distinct from our macroscopic experiences. This was the first fissure in the seemingly seamless classical understanding, a subtle crack that would eventually expose an entirely new, inherently probabilistic, and deeply interconnected reality. Planck's initial quantum leap, born out of necessity to reconcile theoretical predictions with experimental observations, became the pivotal precursor for subsequent groundbreaking discoveries. His work enabled Albert Einstein to brilliantly explain the photoelectric effect, demonstrating light's particulate nature as photons. Later, Niels Bohr utilized the concept of quantized energy levels to account for the stable, distinct orbits of electrons within atoms. Each of these successive insights, building upon Planck's pioneering idea, progressively chipped away at the classical worldview, revealing a universe granular at its very core. It was this unfamiliar physics, rooted in these early daring insights, that would ultimately lead to the startling predictions of superposition, intrinsic uncertainty, and most profoundly, the baffling reality of quantum entanglement. The revolutionary ideas of quantum mechanics, sparked by Planck's quantum leap, rapidly began to redefine our cosmic understanding. Yet for all its predictive power and explanatory elegance, this strange new physics elicited profound unease, particularly from one of the greatest scientific minds of all time, Albert Einstein. The man who had revolutionized our understanding of space-time and gravity found himself deeply troubled by the implications of the quantum realm, especially its probabilistic nature and the bewildering phenomenon of entanglement. Einstein, a staunch proponent of a deterministic, locally real universe, found the core tenets of quantum mechanics deeply unsettling. He believed that physical properties should have definite values independent of observation, and that any influence between distant objects must travel through space at a finite speed. The idea that a particle could exist in a fuzzy superposition of states until measured, or that two particles could be instantaneously linked across vast distances without any classical connection, struck him as incomplete, even absurd. His famous quote, "God doesn't play dice with the universe," encapsulates his profound discomfort with quantum mechanics' inherent reliance on probability rather than absolute certainty. He yearned for a universe governed by elegant, unambiguous laws, where every effect had a clear local cause. His skepticism wasn't a dismissal of quantum mechanics' successes. He himself contributed fundamentally to its early development, notably with his explanation of the photoelectric effect, which validated Planck's quantum hypothesis. However, Einstein maintained that quantum mechanics, for all its predictive power, was merely an effective but ultimately incomplete description of reality. He posited that there must be hidden variables, unseen properties, or mechanisms that, if discovered, would restore the classical principles of determinism and locality, eliminating the need for quantum weirdness. He believed a deeper, more fundamental theory lay beneath the surface, one that would provide a complete non-probabilistic account of every particle's state at all times. Entanglement in particular became a focal point of his discontent. Its apparent spooky action at a distance seemed to directly contradict his theory of special relativity, which strictly forbade faster-than-light communication. If quantum mechanics was correct about entanglement, then something fundamental about his understanding of reality or causality had to be wrong. This philosophical and scientific struggle became a lifelong pursuit for Einstein to find a more complete theory that would reconcile the strange quantum world with the intuitive deterministic cosmos he so deeply believed in. His intellectual battle against entanglement, far from being a weakness, became a powerful catalyst for physicists to truly interrogate the nature of reality. While Albert Einstein wrestled with the quantum realm's probabilistic nature and the bewildering implications of entanglement, another intellectual titan, Niels Bohr, championed an entirely different perspective. Bohr, the visionary Danish physicist, along with his colleagues in Copenhagen, forged what would become known as the Copenhagen interpretation, the predominant and enduring framework for understanding quantum mechanics. In stark contrast to Einstein, Bohr asserted that the inherent strangeness of the quantum world was not a sign of theoretical incompleteness, but rather a fundamental, inescapable truth about reality itself. Central to the Copenhagen interpretation is the radical assertion that quantum properties, such as a particle's position or its spin, do not possess definite values until they are measured. Prior to observation, they exist in a fluid superposition of all possible states. The act of measurement, according to Bohr, is not a passive act of discovery. It actively intervenes, forcing the quantum system to relinquish its myriad possibilities and collapse into a single definite state. This means crucially that at the quantum level, there is no objective reality entirely independent of the interaction that reveals it. The observer, or more precisely, the measurement apparatus, becomes an integral part of shaping the observed reality. Bohr also steadfastly advocated for the principle of complementarity. This profound idea states that certain pairs of quantum properties, like a particle's wave-like and particle-like behaviors, or its exact position and precise momentum, cannot be simultaneously observed or known with perfect accuracy. Probing one aspect inevitably renders the other inherently uncertain. This isn't a deficiency in our technology, but an intrinsic feature of quantum reality itself. The more sharply we define one aspect, the more blurred the other becomes. For Bohr, this inherent trade-off was not a problem to be solved, but a foundational characteristic of the universe's deepest workings. For Einstein, a universe governed by probabilities where observation played such an active and seemingly bizarre role, and where entanglement hinted at non-local influences, was deeply unsatisfying. He engaged in decades of intense, celebrated debates with Bohr, relentlessly arguing for a more deterministic, locally real, hidden variable theory. Yet Bohr, with an unshakable conviction, steadfastly defended the Copenhagen interpretation. He maintained that our classical language and everyday tools, while necessary for describing experiments, simply could not fully capture the underlying quantum reality without profound conceptual shifts. For Bohr, the quantum world wasn't concealing any deeper classical secrets. Its true nature simply was that strange. This profound philosophical schism defined the central intellectual conflict of quantum physics for much of the 20th century, culminating in ingenious experimental designs poised to ultimately test these competing visions of reality. Niels Bohr and the Copenhagen interpretation championed the inherent oddities of quantum mechanics. Yet Albert Einstein, firm in his belief in a deterministic, locally real universe, remained profoundly unsatisfied. This profound dissatisfaction culminated in 1935, when alongside his collaborators Boris Podolsky and Nathan Rosen, he published a groundbreaking thought experiment, now famously known as the EPR paradox. This paper was not an attempt to outright refute quantum mechanics, but rather to expose what Einstein considered its fundamental incompleteness, particularly concerning entanglement. The EPR paradox meticulously crafted a hypothetical scenario presenting a stark choice. Either quantum mechanics was incomplete, missing hidden variables that fully described reality, or it implied a non-local interaction, the very spooky action at a distance, that defied the principles of relativity. Einstein and his co-authors posited two particles perfectly correlated through entanglement that then travel far apart. They argued that if one could measure a property of the first particle, say its position, and instantaneously infer the complementary property of the second particle, its momentum, without disturbing it, then both properties must have pre-existed. Their reasoning rested on two core assumptions. They held sacrosanct realism, the belief that particles possess definite properties regardless of observation, and locality, the principle that influences are restricted to direct contact or propagate at finite speeds. For them, the instantaneous correlations predicted by entanglement, if reality was truly local and real, could only be explained if the particles possessed predetermined hidden variables from their moment of creation. Without such variables, quantum mechanics implied an unphysical instantaneous influence between distant particles, a concept anathema to Einstein's carefully constructed theories. Thus, the EPR paradox presented a profound dilemma: accept a universe that was either fundamentally non-local or one where our most successful theory of matter was profoundly incomplete. This meticulously structured thought experiment profoundly sharpened the philosophical debate, laying down a clear challenge for quantum theory to either accommodate hidden variables or definitively reconcile with its baffling non-local nature. It became a powerful intellectual weapon in Einstein's lifelong battle against the perceived probabilistic chaos of the quantum world. Albert Einstein, despite his monumental contributions to the quantum realm, never truly found peace with its most peculiar tenets. His profound reservations, culminating in the EPR paradox, found their most enduring and iconic expression in a single memorable phrase: spooky action at a distance. This was no mere casual remark. It was his deeply felt repudiation of quantum entanglement's non-local correlations, a direct challenge to what he perceived as a fundamental absurdity inherent in the very laws of the universe. For Einstein, a cosmos governed by principles of local realism dictated that objects could only influence each other through direct contact or by interactions that propagated through space at a finite measurable rate, specifically never exceeding the speed of light. Yet entanglement, with its instantaneous mirroring of properties across vast cosmic gulfs, seemed to flout this deeply held tenet. If measuring a particle on Earth immediately defined the state of its twin, say on Alpha Centauri, with no physical signal traversing the void, then to Einstein, it implied some unseen, non-physical influence acting instantaneously. This defied all classical notions of causality and the sacred cosmic speed limit of his own theory of relativity. This was the spookiness he referred to. His intellectual distress wasn't just a matter of philosophical inclination. It was rooted in a profound logical conviction. Einstein contended that if quantum mechanics truly provided a complete description of reality, then these instantaneous correlations compelled a universe where distant events could affect each other without any local intermediary, a concept he deemed intolerable. He maintained that if such precise correlations existed, they must be attributable to some underlying predetermined hidden variables that the particles carried from their shared origin, thereby preserving both locality and realism. Otherwise, the only alternative was a cosmos fundamentally non-local, a prospect he found untenable. This potent phrase, spooky action at a distance, thus encapsulated the formidable challenge entanglement presented to the burgeoning field of quantum mechanics. Far from being a mere turn of phrase, it became the rallying cry for a generation of physicists who sought either to uncover a flaw in quantum theory or to reveal a deeper, more deterministic layer of reality beneath its probabilistic surface. The very simplicity of Einstein's words belied the profound intellectual battle at stake, a struggle for the very essence of physics compelling the scientific community to confront whether the universe was indeed a locally real, predictable machine, or something infinitely more bizarre, intricately connected, and fundamentally uncertain. Einstein's famous rejection of entanglement, captured in his phrase, spooky action at a distance, sprang directly from his unwavering commitment to a philosophical framework known as local realism. This deeply embedded concept in classical physics is built upon two foundational pillars that shaped our historical understanding of reality. The first is realism, the profound conviction that physical objects inherently possess definite properties and states regardless of whether or not we observe them. A distant star, for instance, has a fixed position and luminosity, whether our telescopes are pointed at it or not. Its attributes are intrinsic, existing independently of any act of measurement. The second pillar is photon, locality. The principle that influences or interactions can only occur between objects that are in direct contact or through forces that propagate across space at a finite speed, a speed that can never exceed the universal constant of light. An event in one location cannot instantaneously affect an event in another distant location. This forms the very bedrock of causality. No effect can arise before its cause, and no action can instantly ripple across the vastness of the universe. Together, realism and locality define the classical worldview, depicting a predictable objective cosmos where information transfer is perpetually constrained by the cosmic speed limit. Yet quantum mechanics, with its intrinsic probabilistic nature, its particles existing in superpositions, and especially its entanglement, appeared to fundamentally shatter both these pillars. For Einstein, the notion that a particle's property, such as its spin, lacked a definite value until measured directly assaulted realism, and the instantaneous correlation between entangled partners, where observing one immediately determined the state of another far removed, starkly broke locality. This implied a direct, unmediated communication faster than light, a concept strictly forbidden by his own theories of relativity. He found this irreconcilable. For Einstein, a truly complete and rational physical theory had to uphold local realism. Therefore, if quantum mechanics accurately predicted entanglement, then it could only be an incomplete theory. This necessitated the existence of hidden variables, undiscovered information or properties that particles carried from their moment of shared creation, which would predetermine their observed states. Such hidden variables would preserve both realism and locality, making the quantum correlations merely appear instantaneous, because our knowledge of these pre-existing properties was lacking. Thus, the profound challenge of local realism became the central battleground. The intellectual struggle extended beyond the accuracy of equations. It became a contest over the very nature of existence. Was the universe fundamentally local and real with quantum mechanics, merely an incomplete description? Or did quantum mechanics unveil a deeper, more astonishing truth, that reality at its most fundamental level is intrinsically non-local, and properties truly gain definition only through interaction? This profound choice, dramatically revealed by entanglement, galvanized physicists to conceptualize and execute groundbreaking experiments poised to definitively test these competing visions of the universe. The intense debate over local realism versus quantum mechanics' non-local probabilistic universe spurred physicists to craft increasingly vivid thought experiments designed to illuminate the profound philosophical quandaries at stake. One such brilliant yet deeply unsettling illustration emerged from Erwin Schrodinger, a foundational figure in quantum theory in 1935. To expose the seemingly absurd implications of quantum superposition and entanglement when extrapolated to the macroscopic world, he devised his now iconic thought experiment, Schrödinger's cat. Schrödinger's setup asks us to imagine a sealed steel box entirely opaque to external observation. Inside this box, a living cat is placed alongside a diabolical device. This mechanism incorporates a single radioactive atom, which, due to the inherent uncertainty governing quantum decay, has precisely a 50% chance of decaying within a 1-hour period. If the atom decays, it triggers a Geiger counter, which in turn activates a hammer, smashing a small flask containing hydrocyanic acid, a deadly poison. Conversely, if the atom does not decay, the flask remains intact, and the cat lives unharmed. Now consider the state of that radioactive atom. According to the principles of quantum mechanics, until it is observed, it exists in a superposition of two possibilities, both decayed and not decayed simultaneously. This is the very essence of being and not being we explored earlier. But here is where Schrödinger pushed the logic to its disquieting conclusion, because the atom's quantum fate is intrinsically linked to the macroscopic fate of the cat. The cat itself, as long as the box remains sealed, also exists in a superposition. The cat is simultaneously alive and dead. This thought experiment was never intended for practical execution. Its true purpose was to highlight the immense conceptual difficulty in applying quantum principles designed for the subatomic to everyday objects. It dramatically illustrates how the inherent fuzziness and probabilistic nature of the quantum realm, particularly superposition, can propagate upwards. When a quantum event is entangled with a macroscopic outcome, like the life or death of a feline, the macroscopic object itself enters a state that profoundly defies our common-sense experience of a definitive singular reality. The paradox for Schrödinger, and for many physicists, was stark. How can an object as unequivocally macroscopic as a cat simultaneously occupy such an indeterminate dual state? The experiment vividly spotlights the notorious measurement problem in quantum mechanics. Precisely when does the superposition collapse? At what point does the probabilistic quantum world transition into the definite classical reality? We observe Schrödinger's feline friend thus became the enduring symbol of quantum mechanics' radical departure from classical intuition, a potent, uncomfortable reminder that reality at its deepest level might be far stranger than our macroscopic minds are equipped to fully perceive. Schrödinger's cat, that infamous thought experiment, thrusts the abstract strangeness of quantum mechanics directly into our tangible world. The stark setup, a cat sealed in a box with a quantum-triggered poison, forces us to confront the bizarre implications of superposition extended to a macroscopic scale. The central unsettling paradox is this: as long as the box remains closed and unobserved, the cat exists in an indeterminate state. It is by quantum definition simultaneously both alive and dead. This is far more than a simple lack of knowledge about the cat's condition. If it were merely our ignorance, the situation would be no different from a sealed container holding a flipped coin. We may not know if it's heads or tails until we look, but it is definitively one or the other. In Schrödinger's scenario, the cat's very existence is quantum mechanically bound to the radioactive atom, which, as we've learned, resides in a superposition of decayed and undecayed states. Due to this intricate quantum linkage, the cat itself, while unobserved, inhabits a probabilistic blend of life and death, a disturbing fuzzy combination of two mutually exclusive outcomes. This hypothetical setup vividly illustrates how the profound uncertainty of the quantum realm can propagate upwards, entangling an entire macroscopic system. The atom's quantum state is not merely connected to the Geiger counter. It is intertwined with the hammer, the poison flask, and ultimately the cat itself. Before the box is opened, the entire system atom device and living creature exists in a unified indeterminate superposition. The cat possesses no independent definitive reality. Its singular state remains suspended in a quantum limbo, awaiting an external interaction to compel its resolution. This thought experiment compels us to confront one of quantum mechanics' most profound and unresolved challenges, the measurement problem. When precisely does this transition from quantum superposition to classical certainty occur? When does the cat cease to be both alive and dead and become definitively one or the other? Is it the moment the atom decays, when the Geiger counter registers, when the hammer strikes the flask, or only when we, the conscious observers, open the box and peer inside? Schrödinger's chilling illustration stands as an enduring symbol of the deep conceptual chasm between the inherent indefiniteness of the quantum world and our classical experience of a fixed, unambiguous reality. It is a powerful reminder of how inextricably intertwined observation might be with the very fabric of existence. Schrödinger's cat vividly illustrates the profound conundrum of superposition. How can a macroscopic entity persist in such an indeterminate dual state? The key to resolving this paradox, at least within the widely accepted Copenhagen interpretation, lies in the pivotal role of measurement, specifically in the phenomenon known as the collapse of the wave function. As previously discussed, a quantum system existing in superposition is mathematically described by a wave function that encompasses all its potential states simultaneously. In Schrödinger's unsettling thought experiment, the atom's wave function describes it as both decayed and undecayed. This in turn entangles it with the cat, whose wave function then describes it as simultaneously alive and dead. Yet this is precisely where our classical intuitive reality diverges from the quantum. We never observe a cat that is both alive and deceased. The moment we open the box, we invariably see one definite outcome, either a healthy living cat or a deceased one. This abrupt transition from a probabilistic superposition of possibilities to a single definite state is precisely the collapse of the wave function. The act of measurement, whether performed by a human observer or an interacting classical apparatus, compels the quantum system to choose one of its potential realities. Before the measurement, countless possibilities coexist. After the measurement, only one specific outcome is actualized. The inherent fuzziness of the quantum realm crystallizes into the concrete reality we perceive. Essentially, the wave function, which governs the probabilities, instantly reduces to a single state, thereby defining the final observable reality. The profound philosophical question that persists fueling ongoing scientific debate centers on precisely what constitutes a measurement sufficient to trigger this collapse. Is it the interaction with a detector, the act of conscious observation, the irreversible recording of information? While various interpretations of quantum mechanics offer differing perspectives, the empirical fact remains undeniable. Quantum systems, when subjected to observation, consistently yield definite results, emerging from a state of indefiniteness. The cat, once suspended in its bizarre quantum limbo, is unequivocally either alive or dead the instant the box's contents are revealed. This collapse of the wave function is not merely an abstract theoretical construct, Its effects are directly observed and meticulously verified in countless experiments. When we attempt to pinpoint a particle's position, its wave function previously diffused collapses to a specific point. When we measure an entangled particle's spin, its superposition collapses, and its partner's superposition simultaneously collapses into the complementary state. This fundamental mechanism is central to both resolving the cat paradox and understanding how the probabilistic quantum world interacts with our definite classical reality. It is a critical concept highlighting the active role of observation in shaping reality at its most fundamental level, and it remains one of the most mysterious and debated aspects of quantum theory. The measurement problem so starkly illuminated by Schrödinger's cat brought into sharp focus the profound philosophical schism that gripped the physics community for much of the 20th century. This was no mere academic disagreement over mathematical interpretations. It was an existential struggle concerning the fundamental nature of reality itself. At stake were bedrock questions about objectivity, determinism, and the startling role of observation, or perhaps even consciousness, in shaping the physical world. On one side stood the proponents of local realism, spearheaded by Albert Einstein, who passionately argued for a universe where properties existed independently of any observation, and where influences propagated no faster than the speed of light. For them, the probabilistic and non-local aspects of quantum mechanics, particularly entanglement, clearly signaled an incompleteness. They believed a deeper, more deterministic layer of reality remained hidden, waiting to be unearthed. Their conviction was that our current theoretical descriptions were simply insufficient to grasp the true, pre-existing states of particles. On the formidable opposing side were the architects of the Copenhagen interpretation, most notably Niels Bohr, who asserted that the very weirdness was the reality. For them, quantum mechanics stood as a complete theory, and its probabilistic nature, the phenomenon of superposition and non-local correlations, were irreducible fundamental truths about the universe. They posited that a particle genuinely existed in a state of indefinite possibilities until measured, and that the act of measurement itself actively instigated the collapse of this wave function, forcing a definite reality into existence. This perspective implied a universe where our very act of probing affected the outcome, a radical departure from the detached objective observer model of classical science. This intellectual chasm extended far beyond the confines of physics, spilling into the realms of philosophy, and even sparking theological discourse. Did quantum mechanics truly imply that reality was fundamentally subjective? Did it mean the universe only sprang into concrete being through observation? And what precisely constituted an observer? Was it a human consciousness, or simply any interaction with the environment, however subtle? These were not trivial questions. They challenged millennia of human inquiry into our place in the cosmos and the very fabric of existence. The stakes were immensely high, leading to passionate debates that defined an entire era of scientific exploration. The ultimate challenge was clear: could these two fundamentally divergent visions of reality ever be reconciled, or would definitive empirical experiments be required to settle the matter once and for all? The profound philosophical chasm between Einstein's local realism and Bohr's Copenhagen interpretation, heightened by the unsettling implications of entanglement, could not be bridged by theoretical discourse alone. For decades, these intellectual giants and their respective schools of thought engaged in passionate sparring. Yet in the absence of definitive empirical evidence, the fundamental nature of reality remained an open, hotly debated philosophical query. The stalemate demanded a decisive step. These sophisticated theoretical arguments had to be rigorously put to the test. However, conceptualizing and executing experiments capable of definitively settling such a deep, pervasive question posed a truly monumental challenge. How does one precisely engineer a setup to prove whether a particle genuinely exists in a superposition of states prior to measurement, or if it merely conceals pre-existing hidden properties? Moreover, how could one rigorously test the instantaneous non-local correlations of entanglement while absolutely ruling out any possibility of classical communication even at the speed of light? The practical experimental hurdles were formidable, demanding an unprecedented fusion of precision control and ingenious design. Firstly, the very systems under investigation were quantum particles such as electrons or photons, infinitesimally small and incredibly fragile. Their delicate quantum states, particularly superposition and entanglement, are exquisitely sensitive to the slightest environmental interaction. Even a minor disturbance can cause this fragile quantum coherence to collapse, mimicking classical behavior and obscuring the very quantum effects intended for observation. Isolating these particles from decoherence, the loss of quantum properties due to uncontrolled interaction with their surroundings necessitated extreme conditions, ultra-low temperatures, near-perfect vacuum chambers, and highly sophisticated laser manipulation. Secondly, and perhaps most critically for the empirical validation of entanglement, was the imperative to definitively close what became known as loopholes. If an experiment claimed to demonstrate non-local correlations, skeptics could always propose that some subtle, unseen classical signal might have passed between the particles, or that the experimental setup itself inadvertently introduced biases. Proving true non-locality demanded ensuring that the choices of measurement settings for each entangled particle were made truly independently, and that the measurements themselves occurred faster than any light-speed signal could possibly travel between them. These seemingly insurmountable practical considerations meant that for a considerable time, the direct experimental verification of entanglement remained a distant dream, prolonging the great philosophical divide. The task was not simply to construct an apparatus, but to engineer one capable of truly interrogating the universe at its most fundamental counterintuitive level. The formidable experimental hurdles and the persistent philosophical deadlock surrounding local realism lingered for decades after Einstein's profound challenges and the EPR paradox. The central question remained stubbornly unanswered. Could science definitively prove whether the universe was governed by local realism, or if entanglement genuinely represented a non-local connection that defied classical intuition? Theoretical arguments continued to clash, yet no one had discovered a means to translate these deep philosophical divergences into a testable empirical hypothesis. Then, in 1964, a groundbreaking insight emerged from an unexpected source, John Stuart Bell, a brilliant Northern Irish physicist working at CERN. Bell wasn't primarily motivated by a desire to simply prove or disprove quantum mechanics. Instead, he harbored a profound fascination with the very foundational questions about the nature of reality that Einstein and Bohr had so passionately debated. His pivotal stroke of genius lay in moving beyond abstract thought experiments to devise a concrete mathematical framework that could for the first time empirically distinguish between the predictions of local realism and those of quantum mechanics. Bell's brilliance manifested in the formulation of a series of mathematical expressions now famously known as Bell's inequalities. These inequalities delineate the maximum possible correlations achievable between two spatially separated particles if the principles of local realism, that is, pre-existing properties and finite speed influences, were true. In essence, Bell precisely quantified the statistical limits on how strongly particles could be correlated if they only communicated locally or relied on hidden predetermined attributes from their origin. He showed that if a specific measurement was performed on a pair of particles, and if their properties were indeed locally real, then the statistical correlation between their observed outcomes could not surpass a particular numerical bound. Crucially, Bell then demonstrated that quantum mechanics, with its predictions of non-local entanglement, foretold correlations that could, under specific conditions, exceed these classical bounds. If subsequent experiments registered correlations stronger than what Bell's inequalities permitted, it would serve as undeniable, irrefutable evidence against local realism. Such a result would imply that either locality was violated, or realism was violated, or perhaps both. This was the decisive key that finally broke the philosophical stalemate. Bell's theorem transformed a century-long philosophical argument into a precise, testable empirical question, providing a clear experimental pathway to interrogate the very nature of reality. It was a theoretical triumph that irrevocably paved the way for the groundbreaking experiments that would forever redefine our understanding of the quantum world, shifting the battle from abstract chalkboard equations to the concrete results of the laboratory. John Bell's groundbreaking insight, elegantly encapsulated in his celebrated inequalities, provided the indispensable mathematical framework to finally resolve the prolonged philosophical debate concerning the fundamental nature of reality. His genius lay in seamlessly translating the abstract concepts of local realism and quantum entanglement into concrete, empirically verifiable predictions. Bell didn't merely propose a theoretical test. He meticulously quantified the expected outcomes under two profoundly divergent assumptions about the universe's operational rules. What Bell precisely predicted was this: if local realism, that is the combination of definite pre-existing properties and interactions limited by the speed of light, were true, then a specific upper limit would constrain the statistical correlations observable between two spatially separated particles. To offer an analogy, imagine you have two distant boxes, each containing an object whose property-like color is predetermined, e.g., one red ball, one blue ball. If these objects were truly classical, then the statistical correlation you could measure between the color of the object in one box and its counterpart in the other would be inherently limited. Bell's inequalities provided the precise mathematical boundaries for such correlations, assuming no instantaneous communication, and that attributes were fixed from the start. He rigorously demonstrated that if hidden variables were indeed at play, secretly dictating outcomes from the moment of their shared creation, then the statistical agreement between measurements on the two distant particles could never exceed a certain value. However, Bell then delivered a stunning counter-prediction. He mathematically showed that if quantum mechanics, with its intrinsic non-local entanglement, was the correct description of reality, then the correlations between measurements on entangled particles could be stronger than those permitted by local realism. In essence, quantum mechanics predicted a statistical agreement that would, under specific experimental conditions, definitively violate Bell's inequalities. This implied that the entangled particles would exhibit a level of synchronized behavior impossible to explain if they were simply carrying pre-existing information and communicating only locally. This was the critical defining juncture. A demonstrable violation of Bell's inequalities would mean that at least one of the foundational tenets of local realism, either locality or realism itself, had to be false. It would constitute undeniable empirical proof that quantum entanglement genuinely represents a non-local connection, where the act of measuring one particle instantaneously influences its distant partner in a manner that defies explanation by any classical hidden information. This groundbreaking theorem transformed an abstract philosophical puzzle into a tangible experimental quest. Bell's work provided a clear quantitative benchmark. Either experimental results would fall strictly within the bounds predicted by local realism, supporting Einstein's vision, or they would shatter those bounds, validating the strange non-local reality predicted by quantum mechanics and the Copenhagen interpretation. This was the ultimate scientific litmus test, offering a definitive pathway to uncover the universe's deepest, most elusive truths. John Bell's revolutionary theorem had transformed a century of philosophical debate into a precise, testable hypothesis. His inequalities provided the crucial mathematical benchmark: either the universe conformed to the bounds of local realism, or it unveiled a deeper, stranger quantum reality, where entanglement truly defied classical expectations. The intellectual stage was set, but now came the truly daunting task: designing and executing the crucial test. The empirical verification that would definitively answer whether local realism held true. This undertaking proved monumental, pushing the absolute limits of experimental physics. The theoretical elegance of Bell's inequalities demanded translation into tangible, meticulously controlled laboratory setups. The primary challenge resided in the extreme fragility of quantum entanglement itself. As we've explored, quantum states are incredibly susceptible to decoherence. Even the most minuscule interaction with the environment can prematurely collapse their delicate superposition, causing them to behave classically, and thus invalidating the very quantum effects one sought to measure. Maintaining entanglement over significant distances and for durations long enough to perform measurements required extraordinary technological ingenuity. Scientists first needed to generate pairs of exquisitely entangled particles, typically photons, which could then be precisely separated and sent to distinct distant locations. Each site would house sophisticated detectors capable of measuring the particle's properties, such as polarization, along different randomly chosen axes. The inherent randomness of these measurement settings was absolutely paramount, designed to prevent any hidden variable or classical signal from influencing or predetermining the outcomes. Furthermore, the measurements at each remote location had to occur so rapidly that there was no conceivable time for any information even traveling at the speed of light to pass between the two detection sites before both measurements were irrevocably completed. This formidable locality loophole represented a particularly difficult challenge to close, demanding unparalleled timing, precision, and substantial physical separation between the measuring devices. Early experiments throughout the 1970s made significant strides, consistently leaning towards quantum mechanics. However, they frequently left open one or more of these crucial loopholes, preventing definitive conclusions that would satisfy the most rigorous skeptics. The scientific community thus yearned for a truly loophole-free Bell test, an experiment so robust, so meticulously designed and executed that it could unequivocally rule out all conceivable classical explanations for the observed correlations. This quest became the ultimate experimental prize, the definitive showdown between Einstein's vision of a locally real universe and the bewildering non-local reality predicted by quantum entanglement. The challenge was immense, but the stakes, nothing less than the fundamental nature of reality, were even higher. The arduous quest for a definitive loophole-free Bell test pushed the technological frontiers of the mid-20th century to their absolute limit. While earlier experiments by pioneering physicists like Stuart Friedman and John Clauser had already provided compelling evidence against local realism, they often left open critical loopholes that prevented an absolute, unimpeachable conclusion. The scientific community eagerly awaited an experiment so meticulously conceived and executed that it could unequivocally nullify these remaining classical explanations. That pivotal moment finally arrived in the early 1980s, driven by the groundbreaking work of French physicist Alain Aspect and his team. Aspect's series of experiments conducted at the Institute of Optics in Orsay, France, marked a profound scientific leap. He and his collaborators specifically targeted the most significant remaining challenges, particularly the pervasive locality loophole. This flaw raised the possibility that the two widely separated detectors, even with seemingly random settings, might still communicate classically, influencing each other's choices, before measurements were completed. To overcome this aspect, engineered an ingenious experimental setup. His team generated pairs of exquisitely entangled photons originating from excited calcium atoms. These photons were then directed along opposite paths to two independent detector stations, separated by several meters. Crucially, before the photons reached their respective detectors, Aspect introduced a truly revolutionary mechanism: ultra-fast optical switches. These switches, controlled by independent, rapidly firing random number generators, could alter the measurement settings on each detector after. The photons had already left their source, but before they arrived at the detection points. This innovative design ensured that the choice of measurement direction for one photon could not possibly influence the other, even if information were somehow traveling at the speed of light. The settings were genuinely independent, determined on the fly, eliminating any predetermination. The results, when finally tallied, were simply unequivocal. Aspect's team consistently observed correlations between the entangled photons that robustly and significantly violated Bell's inequalities. The statistical agreement between these distant measurements proved far stronger than anything local realism or any proposed hidden variable theory could account for. This was the first truly definitive experimental proof of entanglement, providing formidable evidence for the non-local nature of quantum mechanics. It confirmed with unprecedented rigor that the universe indeed operates by the strange interconnected rules predicted by quantum theory, decisively triumphing over Einstein's classical objections. Aspect's breakthrough was a watershed moment, finally bringing an end to decades of theoretical stalemate and irrevocably reshaping our most fundamental understanding of reality. Alan Aspect's pioneering experiments in the early 1980s provided the most compelling evidence yet for quantum entanglement, decisively violating Bell's inequalities and offering robust support for quantum mechanics over local realism. Yet in the rigorous pursuit of scientific truth, absolute certainty demands relentless scrutiny. The broader scientific community, adhering to the highest standards of skepticism, immediately began to dissect Aspect's findings, meticulously searching for any residual vulnerabilities, any subtle loopholes that might still permit a classical explanation for the observed correlations. This healthy scientific skepticism, far from being a hindrance, fueled a new wave of ingenious experimentation, relentlessly pushing the very boundaries of what could be empirically tested. While Aspect had brilliantly closed the crucial schism, locality loophole. With his rapid switching devices ensuring measurement settings were truly independent, after photon emission, other potential avenues for classical explanations persisted. One significant point of contention was the detection loophole, sometimes referred to as the fair sampling loophole. This critique questioned whether the detectors used were truly capturing a representative sample of all entangled particles. If the detectors were inefficient, registering only a small fraction of the photons, and if those detected photons somehow preferentially exhibited quantum correlations, while the vast majority remained unmeasured or behaved classically, then the observed violation of Bell's inequalities could still be classically explained. To decisively close this, subsequent experiments demanded detectors with unprecedented efficiency, capable of capturing a near-total population of the emitted entangled particles. Another more elusive challenge was the freedom of choice loophole, also known as the measurement choice loophole, or the profound concept of superdeterminism. This argument posited that perhaps the ostensibly random number generators used to select measurement settings were not truly random, but were instead subtly predetermined by some cosmic hidden influence, or correlated with the experimental setup in a way that ensured the observed correlations, even if non-local. To rigorously address this, later experiments deployed increasingly sophisticated methods for randomizing measurement choices, some even utilizing light from distant quasars or the faint cosmic microwave background radiation to ensure that the choices were made utterly independently of any earthly influence, thereby rendering any classical predetermination impossible as an explanation for the outcomes. The relentless pursuit of a truly loophole-free Bell test transformed into a global scientific imperative. Dedicated teams of physicists across the world committed themselves to designing and executing experiments that could simultaneously close all known loopholes, leaving no room for classical doubt. This unwavering drive for absolute certainty was a testament to the profound implications of the debate. If entanglement proved truly non-local, it would fundamentally reshape not just physics, but our entire understanding of the universe. The stakes were too immensely high to tolerate any lingering ambiguity. These subsequent, increasingly refined experiments, building upon Aspect's foundational work, would push quantum technology and experimental design to unprecedented frontiers, bringing us ever closer to an undeniable truth about the very nature of reality. Alain Aspect's experiments in the 1980s marked a monumental stride, delivering the first truly definitive evidence against local realism. Yet the rigorous pursuit of scientific truth demands unyielding scrutiny. The broader scientific community, upholding the highest standards of skepticism, immediately began to dissect Aspect's findings, meticulously seeking any lingering vulnerabilities, any subtle loopholes that might still permit a classical explanation for the observed quantum correlations. This healthy scientific skepticism, far from being an impediment, galvanized a new generation of ingenious experimentation, ceaselessly pushing the very boundaries of what empirical physics could test. A leading figure in this relentless pursuit was Anton Zeilinger and his team in Vienna, Austria. Building upon Aspect's foundational work, Zeilinger's group conducted a series of increasingly precise experiments. In 1998, they performed a Bell test using entangled photons separated by hundreds of meters, significantly extending the reach of the locality loophole. Their results consistently violated Bell's inequalities, even with the expanded spatial separation, providing further compelling evidence. However, the detection loophole, the concern about whether detectors were truly sampling all entangled particles representatively, remained a significant challenge. This was finally addressed by the groundbreaking work of a team led by Ronald Hansen at Delft University of Technology in the Netherlands in 2015. Their revolutionary experiment utilized entangled electron spins in diamond defects a departure from photons. Crucially, they achieved detector efficiencies high enough to simultaneously close both the detection and locality loopholes. Their results unequivocally violated Bell's inequalities, marking the first time these two critical loopholes were closed in a single monumental experiment. Adding further layers of irrefutability, other research groups continued to push the conceptual and technological boundaries, developing what became known as cosmic loophole-free Bell tests. For instance, in 2017, pioneering teams led by David Kaiser at MIT and Anton Zeilinger leveraged light from distant quasars and the faint cosmic microwave background radiation to determine the measurement settings for entangled photons. This ensured that the choices of measurement were truly independent, inherently free from any terrestrial influence or hidden variables that might have been correlated since the very dawn of the universe. The sheer cosmic randomness ensured the freedom of choice loophole was decisively slammed shut. Across a diverse array of quantum platforms, from entangled photons and trapped ions to superconducting qubits and diamond defects, and over ever-increasing distances, the experimental results have consistently converged on the same astonishing conclusion the correlations predicted by quantum mechanics are undeniably real, and they unequivocally violate local realism. These modern confirmations represent a profound triumph of experimental physics, meticulously dismantling every conceivable classical alternative and providing irrefutable, overwhelming evidence for the existence of quantum entanglement. The battle of ideas that began with Einstein's profound unease has now been settled not by philosophical debate, but by the relentless, precise interrogation of reality itself. The meticulous efforts of Alan Aspect, followed by the groundbreaking experiments of Ronald Hansen, Anton Zeilinger, and numerous other dedicated research teams worldwide, have culminated in an undeniable torrent of evidence. For decades, with ever more sophisticated technology and increasingly rigorous experimental designs, the collective results have converged into a singular, irrefutable picture. The fundamental debate that once divided the scientific community, the profound philosophical chasm between Einstein's local realism and the predictions of quantum mechanics, has now been definitively settled by empirical fact. From the pioneering Bell tests of the 1970s and 80s to the meticulously designed loophole-free experiments of the 2010s and beyond, the data consistently, powerfully, and unequivocally demonstrates the same astonishing truth: quantum entanglement is real. Its observed correlations systematically defy the statistical limits set by Bell's inequalities, revealing an interconnectedness that no classical, local, or realistic theory can explain. Every plausible escape route, be it the locality loophole, the detection loophole, or the freedom of choice loophole, has been systematically and painstakingly eliminated, leaving no credible classical alternative to account for the observed phenomena. This global scientific consensus is not merely founded on a handful of isolated successes, but on an expansive, cumulative body of evidence as robust and compelling as any in the entire field of physics. Researchers employing a diverse array of quantum platforms ranging from entangled photons and trapped ions to superconducting circuits and electron spins in diamond have all arrived at the identical conclusion. Their experiments span distances from a few meters within a controlled laboratory to hundreds of kilometers via fiber optic networks, and even thousands of kilometers through satellite-based links. This remarkable consistency across varied methodologies and vast spatial separations speaks volumes about the universal validity of this perplexing phenomenon. The implications are profound. This wealth of data unequivocally tells us that the universe at its most fundamental level is intrinsically non-local. The properties of entangled particles are not merely predetermined from their shared inception, nor do they communicate through any classical means. Instead, their quantum states are profoundly and perpetually intertwined, forming a single unified quantum whole. The act of measuring one particle instantly without any physical signal influences the reality of the other, regardless of their separation. This is not a mere laboratory oddity. It is a foundational characteristic of reality itself. This formidable body of scientific work has irrevocably confirmed what once seemed like the most bizarre predictions of quantum theory. It has brought a definitive resolution to one of the most significant intellectual debates in modern science, firmly establishing quantum entanglement as an experimentally verified, undeniable truth. The universe we now definitively know is far stranger and more fundamentally interconnected than our everyday intuition could ever suggest, operating by rules that elegantly defy classical common sense. We have confirmed that the quantum realm is not merely an abstract theoretical construct, but a living, pulsating reality that continues to unveil its deeper wonders. After decades of profound theoretical struggle, after ingenious thought experiments, and the relentless pursuit of technological mastery, the intellectual battle for the very nature of reality has at last reached its definitive resolution. The heated contest between Albert Einstein's cherished local realism and the perplexing predictions of quantum mechanics, particularly concerning entanglement, is now unequivocally settled. The universe itself, through painstakingly constructed experiments, has delivered its irrefutable verdict. Quantum is real. For generations, the concept of spooky action at a distance lingered as a challenging enigma, a mathematical oddity that seemed to mock classical common sense and the very fabric of space-time. Einstein, with his unparalleled intellect, championed a more complete deterministic vision, proposing hidden variables that would restore a comforting sense of local reality. Conversely, Niels Bohr steadfastly embraced the inherent quantum weirdness, accepting its probabilistic nature and the active role of observation as fundamental truths. Their philosophical schism, a titanic clash of worldviews, left the scientific community suspended in a state of profound, tantalizing uncertainty. But physics at its heart is an empirical science. Abstract arguments, no matter how elegant, must ultimately bow to the irrefutable weight of experimental evidence. The Bell tests, ignited by John Bell's brilliant theoretical insight and meticulously brought to fruition by pioneers like Alain Aspect, then continuously refined by a global consortium of dedicated physicists, including Anton Zeilinger and Ronald Hansen, have provided that undeniable answer. These remarkable experiments systematically dismantled every classical loophole, the possibility of sub-light-speed communication between detectors, the locality loophole, the concern about inefficient particle capture the detection loophole, and even the subtle influence on random choices, the freedom of choice loophole. Each successive, increasingly sophisticated test closed yet another avenue for a classical explanation, pushing the very limits of experimental precision and human ingenuity. The cumulative weight of this formidable evidence is now overwhelming, leaving absolutely no credible room for doubt. Time and again, across diverse experimental setups and over distances spanning mere meters to thousands of kilometers, the results have been unfailingly consistent. The correlations observed between entangled particles significantly and systematically violate Bell's inequalities. This is the undeniable empirical proof. It means that the universe at its most fundamental level does not operate according to the comforting, intuitive rules of local realism. Therefore, we can now confidently assert that quantum entanglement is far more than a theoretical curiosity, a perplexing paradox confined to academic discourse. It stands as a rigorously proven fundamental phenomenon, an intrinsic aspect of the cosmos. Particles are indeed inextricably linked, sharing an instantaneous bond that transcends the classical limitations of space and independent existence. The act of measuring one entangled particle genuinely does, in that precise moment, influence the reality of its distant partner, not through some faster-than-light signal, but because they remain in a profound quantum sense, a single indivisible system. This profound truth, once so deeply unsettling, has now become a cornerstone of our scientific understanding. The universe truly is more wondrously interconnected and more fundamentally enigmatic than our macroscopic experience could ever have suggested. The intellectual battle for reality's very definition has been decisively won, ushering in a new era of certainty about the astonishing nature of the quantum realm. We have unraveled this mystery, and the implications for both fundamental science and groundbreaking technology are nothing short of revolutionary. The exhaustive, meticulous experimentation conducted across laboratories worldwide has now delivered its incontrovertible verdict. The fundamental nature of reality, once the subject of fervent philosophical contention and decades of rigorous scientific inquiry, has been clarified with astonishing precision. With the full, undeniable weight of empirical evidence, we can now declare quantum entanglement is not merely a theoretical construct or a baffling paradox. It is an intrinsic, experimentally verified feature of our universe. The intellectual battle initiated by Einstein's profound skepticism and sharpened by Bell's ingenious theorem has culminated in a decisive triumph for the quantum description of reality. Every conceivable classical explanation, every ingeniously devised loophole has been systematically dismantled by the relentless march of scientific discovery. The precise correlations meticulously observed between entangled particles consistently exceeding the statistical limits set by Bell's inequalities demonstrate beyond any credible doubt that reality at its most fundamental level is indeed non-local. Particles once entangled share an immediate unified existence, their individual fates inextricably linked across vast distances with no classical communication required to bridge the cosmic expanse. This profound interconnectedness is not an artifact of our measurement techniques, nor a subtle trick of nature. It is the universe revealing a deeper, more profound unity than our macroscopic senses could ever intuit. This hard-won truth signifies that the mystery has been unraveled. The perplexing enigma, once known as spooky action at a distance, has transitioned from an unsettling philosophical quandary into a rigorously proven cornerstone of modern physics. We no longer grapple with if entanglement exists, but rather with compelling urgency, we turn our focus to how its extraordinary properties can be harnessed. This definitive understanding marks a pivotal shift, propelling us beyond the realm of pure scientific inquiry and directly into a new frontier of technological innovation. The universe's most enigmatic secret, now unveiled and accepted, transforms into an extraordinarily powerful tool. We stand at the precipice of a new era where the bizarre yet elegant rules of the quantum realm are beginning to yield revolutionary capabilities, poised to redefine computing secure communication and our very interaction with the world around us. With the profound reality of quantum entanglement now unequivocally established by rigorous experimentation, the trajectory of scientific inquiry has undergone a pivotal reorientation. The era of proving if this bizarre connection existed has seamlessly transitioned into the exhilarating challenge of how to precisely harness its extraordinary power. This profound shift has ignited a vibrant and rapidly expanding domain quantum technologies, where scientists and engineers are meticulously devising ways to manipulate and control the subatomic world's most counterintuitive properties for groundbreaking practical applications. For decades, the concepts of superposition, fundamental uncertainty, and entanglement largely resided within the abstract confines of theoretical physics, serving primarily as tools for understanding the universe's deepest workings. Now, however, we are witnessing a remarkable evolution from abstract theory to tangible innovation. Researchers are no longer content merely to observe these quantum phenomena. They are actively designing, constructing, and refining devices that deliberately leverage these properties to accomplish tasks utterly beyond the capabilities of even the most advanced classical technologies. This marks the dawn of an age of actively mastering the quantum realm, bending its wild, elusive nature to our will. This monumental endeavor necessitates overcoming immense technical challenges. Quantum states are exquisitely fragile. The slightest environmental noise, minute vibrations, or stray electromagnetic fields can cause their delicate superposition and entanglement to decohere, collapsing into ordinary classical states and rendering them useless for quantum operations. To circumvent this, scientists are innovating ingenious techniques to isolate quantum systems, often demanding cryogenic temperatures near absolute zero ultra-high vacuums and intricate shielding from all external interference. Simultaneously, they are experimenting with a diverse array of qubit platforms, the quantum analog of classical computer bits, each possessing unique advantages and disadvantages in maintaining coherence from individual atoms and ions precisely trapped by lasers to superconducting circuits, photons and engineered defects within diamonds. The driving force behind this colossal effort is the promise of unprecedented capabilities. By systematically learning to precisely control and interlink entangled particles, we are unlocking entirely new paradigms for computation, secure communication, and ultra-sensitive sensing. These are not incremental improvements on existing technologies, but truly foundational shifts powered by the unique inherent properties of the quantum realm. The era of passively contemplating quantum weirdness is firmly behind us. We are now actively engineering this profound dimension of reality, coaxing its most astonishing attributes to serve humanity's most ambitious scientific and technological goals. This is precisely where the true revolution begins. With quantum entanglement now undeniably proven and its profound reality accepted, the scientific and technological landscape has been irrevocably transformed. The era of merely confirming if entanglement exists has given way to the exhilarating pursuit of how to precisely leverage its extraordinary capabilities. This pivotal shift has ignited a vibrant and rapidly expanding domain, quantum computing, a revolutionary field poised to redefine our understanding of information processing. This is no mere incremental upgrade to our current machines. It represents a radical new paradigm capable of tackling problems that would remain utterly intractable for even the most powerful supercomputers running for epochs longer than the age of the universe. This is the staggering promise of quantum computing. At its very essence, quantum computing diverges dramatically from classical computation. Traditional computers, whether your smartphone or a massive supercomputer, operate on bits units of information that exist in one of two definitive states, 0 or 1. All complex operations are built from sequences of these unambiguous binary choices. Quantum computers, by stark contrast, employ qubits, which harness two extraordinary quantum phenomena we have previously explored: superposition and entanglement. Thanks to superposition, a single qubit can exist not just as a 0 or a 1, but astonishingly as a blend of both 0 and 1 simultaneously. This inherent quantum parallelism means that even a single qubit inherently contains vastly more potential information than its classical counterpart. Now, couple this with entanglement. When multiple qubits become entangled, their destinies become inextricably connected. A measurement on one instantly influences the state of others, forging a complex, interwoven quantum state that represents not just a sum of individual possibilities, but an immense unified network of potential solutions. This unparalleled ability to hold multiple states at once superposition and to be correlated in intricate, non-local ways, entanglement is the wellspring of quantum computers' immense power. While a classical machine must sequentially process each potential solution, a quantum computer, by leveraging superposition, can explore a multitude of possibilities concurrently. Then, through sophisticated quantum algorithms and the manipulation of entangled qubits, it can selectively amplify the probability of correct answers while suppressing incorrect ones. This inherent parallel processing capability allows quantum computers to perform certain calculations at speeds and scales that shatter classical computational limits. The implications for human progress are truly breathtaking. Complex challenges that would currently require classical computers more time than has passed since the Big Bang could theoretically be solved in mere minutes or hours by a sufficiently advanced quantum machine. This is not merely about accelerating existing processes. It is about unlocking entirely new realms of computational possibility. The promise of quantum computing transcends mere speed. It aims to fundamentally redefine what is computable, opening doors to scientific and technological breakthroughs once confined solely to the domain of theoretical imagination. The staggering promise of quantum computing stems directly from its foundational unit of information, the qubit. Unlike the classical bit, which must definitively exist in one of two distinct states, either a 0 or a 1, the qubit leverages the profound quantum mechanical principle of superposition. This allows a qubit to inhabit not just one state or the other, but astonishingly a probabilistic combination of both 0 and 1 simultaneously. To grasp this, consider a classical coin. Once flipped, it is undeniably either heads or tails, even if its face is hidden. A classical bit is precisely like this, a fixed 0 or a fixed 1. Now imagine a quantum coin spinning in the air. While it spins before it lands, it is simultaneously heads and tails, a fluid blend of possibilities. This is how a qubit operates. It embodies all its potential outcomes concurrently. This capacity for quantum parallelism means that a single qubit inherently holds exponentially more information than a classical bit. For instance, while two classical bits can represent only one of 4 states at any given moment, 0, 1, 10, or 11, 2 entangled qubits in superposition can represent all 4 of those states simultaneously. This is where the true exponential power begins to unfold. With n classical bits, you can store n pieces of information. With n qubits operating in superposition, you can hold 2.0n pieces of information at the same time. To put this into perspective, a quantum computer with just 300 perfectly entangled qubits could theoretically process information equivalent to more data than there are atoms in the entire observable universe. This unparalleled capacity to explore multiple computational pathways concurrently is precisely what empowers quantum computers to tackle problems that would overwhelm even the most powerful conventional supercomputers. Furthermore, the full force of this new computational paradigm emerges when these qubits are also entangled. When qubits become entangled, their individual superpositions are intrinsically linked, forming a unified quantum state. A measurement on one entangled qubit instantly influences the states of all others in that connected set. This deep, non-local connection enables quantum computers to perform incredibly complex correlations between computations, a feat utterly impossible for classical machines. While superposition allows qubits to hold multiple values, entanglement provides the crucial mechanism for these values to interact and process information together in highly efficient quantum algorithms. This combined power of qubits, leveraging both superposition and entanglement, dramatically expands computational capability. It's akin to having a vast library where every book can be read simultaneously, and every page within those books is intricately interconnected with every other page. This quantum parallelism and profound interconnectedness are the indispensable keys to solving classes of problems that remain utterly out of reach for classical computers, heralding a truly new era of computational prowess. The inherent power of qubits operating through superposition and entanglement is poised to usher in a truly revolutionary era of computational capability. Quantum computers promise to solve problems currently considered utterly impossible for even the most advanced classical machines. These are not mere incremental advancements. They represent fundamental shifts in what is computationally feasible, promising to accelerate progress across a multitude of critical fields. One of the most profound potential applications lies in accelerating drug discovery and development. Designing novel medicines often entails simulating the complex quantum mechanical interactions between molecules, how a new drug candidate precisely binds to a target protein or its intricate behavior within a complex biological system. Classical computers struggle with these simulations due to the inherent quantum nature of molecular bonds. A quantum computer, by directly mimicking these quantum processes, could accurately model molecular structures and reactions at an unprecedented scale, dramatically speeding up the identification of promising drug candidates, optimizing their efficacy, and predicting potential side effects. This could lead to transformative breakthroughs in treating diseases that currently evade effective therapies. Similarly, quantum computing holds immense promise for designing novel materials. From the elusive dream of superconductors transmitting electricity with zero resistance at ambient temperatures to highly efficient catalysts for industrial processes, and even entirely new forms of energy storage, the fundamental properties of materials are dictated by the quantum behavior of their constituent atoms and electrons. Simulating these intricate quantum interactions from first principles is computationally prohibitive for classical machines. Quantum computers could precisely model these behaviors, enabling the discovery and design of materials with tailor-made properties, revolutionizing industries from energy and electronics to manufacturing and aerospace. Beyond simulation, quantum computers pose a significant existential challenge to much of our existing cryptographic security. Shor's algorithm. A theoretical quantum algorithm has demonstrated that a sufficiently powerful quantum computer could efficiently factor large numbers. This mathematical task currently underpins a vast portion of today's internet security, including the widely used RSA encryption that protects our financial transactions, personal data, and national security communications. This impending threat has already spurred a global race to develop quantum-resistant cryptography, new encryption methods designed to withstand even quantum attacks. Furthermore, quantum computing stands poised to revolutionize artificial intelligence and complex optimization problems. Modern machine learning algorithms often involve navigating colossal, intricate datasets to identify optimal patterns or solutions. Quantum algorithms, particularly those leveraging the parallel processing capabilities afforded by superposition and entanglement, could explore these immense solution spaces far more efficiently. This could lead to dramatic breakthroughs in areas such as advanced pattern recognition, natural language processing, and the development of truly intelligent AI systems. For complex optimization challenges ranging from global logistics and supply chain management to financial portfolio optimization and urban traffic flow, quantum computers could identify optimal solutions in scenarios where classical approaches are hopelessly bogged down by combinatorial explosion. In essence, quantum computing is not simply a tool for faster number crunching. It represents a new fundamental lens through which to comprehend and manipulate the very rules of the universe at its deepest level. By harnessing its incredible power, we stand at the precipice of solving problems that have long seemed insurmountable, ushering in an era of scientific and technological advancement previously confined to the realm of pure imagination. While quantum computing promises to shatter many of today's most complex cryptographic codes, the very principles of quantum mechanics that enable this unprecedented threat also offer a revolutionary counter-solution: quantum cryptography. This is not about building stronger mathematical fortresses. It is about leveraging the fundamental laws of the universe to achieve absolute, provable security for our communications, a level of certainty previously unimaginable in the digital age. The most prominent application within quantum cryptography is, or SPOR, quantum key distribution, QKD. Unlike classical encryption methods which rely on mathematical complexities that in theory could eventually be overcome by sufficiently powerful computers, including future quantum machines, QKD uses individual quantum particles, typically photons, to establish and transmit encryption keys. The inviolable security of these keys is guaranteed not by computational difficulty, but by the inherent immutable principles of quantum mechanics itself, particularly superposition, and the crucial role of measurement. Imagine two parties traditionally named Alice and Bob, who wish to securely share a secret encryption key. In a QKD protocol, Alice sends Bob a stream of photons, each meticulously prepared in a specific quantum state, representing a 0 or a 1, for instance, distinct polarizations. Bob, upon receiving each photon, randomly chooses a measurement basis. Due to the nature of quantum mechanics, if Bob chooses the correct measurement basis, he will accurately determine the photon's state. However, if he selects the wrong basis, the photon's superposition will randomly collapse, yielding an unpredictable, meaningless result. After receiving the full stream, Bob publicly declares which basis he used for each photon without revealing the actual measurement outcomes. Alice then informs him which of his basis choices were correct. From these perfectly matched choices, they extract a raw, shared, secret key. But what truly renders this key uncrackable? The absolute security hinges on a core tenet of quantum mechanics, the no-cloning theorem, which states that it is fundamentally impossible to create a perfect identical copy of an unknown quantum state. Therefore, if an unauthorized eavesdropper, Eve, attempts to intercept the photons and copy their states, she cannot do so without inevitably disturbing them. Her attempt to measure or duplicate the quantum information will inherently cause the photon's delicate quantum states to collapse or change, introducing detectable errors into the key. When Alice and Bob subsequently compare a small pre-agreed subset of their shared raw key, they can immediately detect these telltale anomalies. If the error rate exceeds a predetermined threshold, they instantly know Eve was listening, and they discard the compromised key, initiating a new exchange. If the error rate remains low, they can proceed with absolute confidence that their key is pristine and entirely secure. This means that any attempt to eavesdrop on a quantum key distribution leaves an undeniable physical footprint. The act of observation, as we learned with wave function collapse, actively alters the quantum system. This provides an unprecedented physics-guaranteed level of security, ensuring that the encryption key shared between Alice and Bob is fundamentally invulnerable, its integrity guaranteed not by the sheer computational difficulty of cracking it, but by the unwavering immutable laws of the universe itself. Quantum cryptography thus promises a future of truly private and secure communication, heralding an era where our most sensitive information can be protected by a shield woven from the very fabric of reality. Having explored how quantum mechanics can deliver fundamentally unbreakable codes through quantum key distribution, our gaze now extends towards an even more ambitious vision: the quantum internet. Imagine a global network not composed of classical bits and data packets, but built upon the profound connections of entangled qubits. Such a web could utterly transform secure communication, unlock unprecedented distributed computational power, and enable entirely novel forms of quantum sensing across immense distances. Our conventional internet transmits classical information streams of zeros and ones across vast stretches of fiber optic cable or through wireless signals. A quantum internet, by stark contrast, would transmit and meticulously maintain fragile, entangled quantum states between geographically separated quantum processors. Its very architecture would comprise networks of quantum nodes, specialized miniature quantum computers, or memory units interlinked by channels capable of robustly distributing and preserving entanglement. This is far more than a mere upgrade. It represents a foundational reimagining of how information can be shared and processed on a global scale, directly leveraging the very spooky action at a distance that once so deeply perplexed Albert Einstein. The foremost and most immediately impactful application of a quantum internet would be the widespread deployment of unconditionally secure communication. While current quantum key distribution (QKD) systems already allow two parties to share an encryption key with physics. Guaranteed security, their range is often limited. Photons traveling through optical fibers experience unavoidable loss, and simply amplifying the signal as is done in classical networks would irrevocably destroy the delicate quantum states. A quantum internet would circumvent this distance limitation by establishing chains of entangled nodes. Through a sophisticated process known as entanglement swapping, a pair of entangled particles can share their entanglement with another pair, effectively extending the quantum link over far greater distances without direct destructive transmission of the quantum state itself. This innovation would enable QKD to operate reliably across intercontinental spans, forging truly unhackable communication channels for governments, financial institutions, and private individuals worldwide. Beyond impenetrable communication, a quantum internet promises to enable distributed quantum computing. Imagine connecting several smaller specialized quantum computers dispersed geographically into a single cohesive and far more powerful virtual quantum machine. Certain immensely complex problems too vast for any single quantum computer to tackle in isolation could be meticulously broken down and processed collaboratively across multiple interconnected quantum nodes. This would prove particularly transformative for highly specialized tasks, allowing researchers to pool their disparate quantum computational resources for incredibly intricate simulations, the development of advanced AI algorithms, or deep scientific discovery. It would constitute a true collaborative computing environment where quantum information is seamlessly shared and processed across vast geographical divides. The vision extends further into other remarkable possibilities. A quantum internet could facilitate a sprawling network of ultra-precise quantum sensors, enabling global-scale measurements with unprecedented accuracy. Imagine arrays of quantum sensors distributed across continents, intricately entangled to detect elusive gravitational waves, subtle dark matter interactions, or minute seismic activity with a sensitivity impossible for isolated sensors. Such a network could also enable highly accurate global quantum clock synchronization, far surpassing the precision of current GPS systems by leveraging the entanglement between atomic clocks distributed worldwide. This advancement would have profound implications for navigation, fundamental scientific research, and even rigorous tests of relativity. Constructing such an intricate global quantum network presents immense technical challenges. Maintaining the fragile quantum coherence of entangled particles over long distances remains incredibly difficult. Quantum repeaters, which are quantum analogs of classical signal boosters, are crucial for extending entanglement across vast stretches. Unlike classical repeaters, these wouldn't amplify the signal, but would create new entangled pairs and then swap entanglement to connect them, building a robust chain of entangled links. Significant research is also vigorously underway on developing stable quantum memory to store qubits for longer durations and high-fidelity quantum transducers to seamlessly convert quantum information between different mediums. For instance, from photons optimized for transmission to trapped ions suitable for processing. Despite these formidable hurdles, the journey towards a practical quantum internet is well underway, with national and international initiatives actively building prototype quantum networks and testing foundational protocols. This represents a bold leap into a future where the counterintuitive principles of the quantum realm are not just academically understood, but intricately woven into the very fabric of our global information infrastructure. It promises a world where connections are inherently secure, computations reach unimaginable scales, and our collective ability to probe the universe achieves unprecedented precision, all thanks to the profound shared fates of entangled particles. The phrase quantum teleportation frequently conjures vivid imagery from science fiction, the instantaneous beaming of Captain Kirk across the galaxy, or the immediate transportation of physical objects from one location to another. While the scientific reality is every bit as astonishing, it is crucial to clarify what quantum teleportation genuinely entails. It is the transfer of quantum information. Specifically, an unknown quantum state from one location to another, not the physical transportation of matter or energy. This remarkable phenomenon represents a direct and vital application of quantum entanglement, poised to become a cornerstone of future quantum communication networks, like the quantum internet. The core principle of quantum teleportation hinges on the prior establishment of an entangled pair of particles between two geographically separated parties. Let's refer to them as Alice and Bob. Alice holds an unknown quantum state she wishes to transmit to Bob, embodied by a message photon, photon M. She cannot simply measure photon M's state and communicate the classical result, because due to the no-cloning theorem, measuring would irrevocably destroy the delicate quantum information. Instead, Alice and Bob first share an entangled pair. Photon A is with Alice, and photon B is with Bob. Photons A and B are entangled, meaning their fates are intrinsically intertwined. Alice then performs a joint measurement on her message, photon M, and her entangled photon A. This specific measurement, known as a Bell state measurement, yields one of four possible classical outcomes, each of which profoundly influences the state of photon B. Crucially, Alice's measurement destroys the original quantum state of photon M. It ceases to exist in its initial form. However, the result of Alice's measurement, which of the four outcomes occurred, is classical information that Alice must then transmit to Bob using a conventional classical channel, such as a radio signal or a fiber optic link. This classical communication remains strictly limited by the speed of light. Upon receiving Alice's classical message, Bob instantly knows precisely which of four possible quantum operations to perform on his entangled photon B. When Bob executes the correct operation, his photon B immediately takes on the exact quantum state that photon M originally possessed. The quantum information, the state itself, has been teleported from photon M to photon B. It's vital to understand that photon M itself did not physically travel, nor was any information sent faster than light. Instead, the pre-existing entanglement between photon A and photon B, combined with the classical communication of the measurement result, allowed Bob's particle to instantly assume the state of Alice's now destroyed particle. This seemingly miraculous transfer of quantum information is pivotal for the advancement of quantum communication. For example, it could be utilized to transfer a qubit from a quantum computer on Earth to one on Mars, without physically sending the qubit itself, circumventing the immense challenges of transmitting fragile quantum states over vast distances. It also powerfully reinforces the bizarre nature of quantum reality. A quantum state is an inherent property, not merely a classical piece of data, and its transfer can occur in this indirect yet profoundly instantaneous fashion. While we remain far from Star Trek-style human teleportation, which would demand the transfer of immense quantities of complex matter and energy, quantum teleportation is a powerful, experimentally verified phenomenon that vividly highlights the profound utility of entanglement in building the quantum technologies of tomorrow. Beyond the revolutionary promises of quantum computing, unbreakable cryptographic codes, and the ambitious vision of a global quantum internet, the profound properties of entanglement extend their reach into an even broader spectrum of emerging fields. Scientists are meticulously exploring how this counterintuitive interconnectedness can be harnessed for super-precise measurements, ultra-sensitive quantum sensing, and for groundbreaking advanced imaging technologies. This marks yet another frontier where the very rules of the quantum realm are fundamentally transforming what is technologically possible. At the heart of these applications lies quantum metrology, the precise science of measurement leveraging quantum effects. Our most accurate classical instruments, from the atomic clocks that govern GPS systems to the highly sensitive magnetometers used in medical diagnostics, rely on the inherent properties of individual atoms or photons. However, by deploying entangled particles, scientists can push the limits of precision far beyond what is classically achievable. This overcomes the standard quantum limit imposed by the inherent noise and uncertainty of individual quantum measurements, because entangled particles sharing a unified quantum state can be manipulated to respond collectively and coherently to external influences, amplifying subtle signals in a way that independent particles cannot. Consider the development of next-generation atomic clocks. Current atomic clocks, the foundation of global timing and navigation, boast incredible precision. Yet their ultimate accuracy is bounded by the quantum noise inherent in individual atoms. By entangling thousands of atoms within an atomic clock, their collective quantum state becomes exquisitely sensitive to external fields and the very flow of time. Any minute deviation, even a minuscule shift due to a change in gravitational potential as predicted by Einstein's relativity, would be instantly amplified across the entire entangled ensemble. Such advancements could lead to atomic clocks so precise they would lose or gain merely 1 second over the entire age of the universe, with profound implications for fundamental physics research, ultra-accurate navigation, and even direct tests of space-time curvature. Entanglement also promises to revolutionize magnetic field sensors. Highly sensitive magnetometers are indispensable for diverse applications, including advanced medical diagnostics such as magnetoencephalography for mapping intricate brain activity, geological surveys for mineral exploration, and detecting subtle changes in planetary magnetic fields. By entangling arrays of nitrogen vacancy centers in diamonds, for example, researchers are engineering sensors that achieve unparalleled sensitivity to magnetic fields. This capability could lead to dramatically enhanced resolution in medical imaging techniques, enabling earlier and more accurate disease detection. In the sphere of advanced imaging, entanglement unveils entirely new possibilities. Classical imaging methods face inherent limitations in resolution and often require substantial light exposure, which can damage delicate biological samples or impede imaging in low-light conditions. Quantum imaging, however, can elegantly bypass these barriers. One particularly fascinating technique is quantum ghost imaging. Here, an image is formed without the object ever directly interacting with the light that ultimately detects it. This is achieved by creating pairs of entangled photons. One photon from the entangled pair interacts with the object, e.g., a fragile biological specimen, and then proceeds unobserved. Its entangled partner, which never interacted with the object, is then measured, and its properties are used in correlation with the first photon's path to reconstruct a remarkably clear image of the object. This allows for imaging with extremely low light levels or in different wavelengths, significantly reducing potential damage to sensitive samples. Furthermore, entanglement could enable TOTIS, sub-shot noise imaging, providing clearer images even in incredibly dim lighting conditions, and even quantum lithography, potentially facilitating the creation of microchips with features far smaller than the classical diffraction limit of light. These innovative techniques exploit peculiar quantum correlations to extract more information from less light-opening doors to visualizing the microscopic world with unprecedented clarity and minimal invasiveness. These nascent applications of quantum entanglement spanning metrology, advanced sensing, and revolutionary imaging paint a truly compelling picture of a future where the counterintuitive principles of the quantum realm are not merely understood academically, but are intricately engineered to profoundly enhance our technological capabilities across virtually every scientific and industrial sector. It reveals a universe where its most baffling connections are now becoming our most powerful tools, pushing the very boundaries of what humanity can measure, perceive, and ultimately achieve. We have now traversed the astonishing landscape of quantum technologies, glimpsing the transformative power of entanglement in revolutionizing computation, securing communication, and enhancing our ability to measure and image the world with unprecedented precision. From tackling intractable problems in drug discovery and material science, to forging truly unbreakable codes and enabling new forms of ultra-sensitive sensing, the practical implications of understanding and meticulously harnessing entanglement are truly staggering. This collective pursuit signifies far more than a mere incremental advancement in technology. It represents the dawn of a completely new technological frontier. For the vast majority of human history, our technological progress has been intricately woven from the predictable macroscopic rules of classical physics. From the Industrial Revolution that reshaped societies to the digital age that now defines our global connections, every invention, every monumental leap forward has been rooted firmly in our understanding of gravity, electromagnetism, and Newtonian mechanics. But now, as we relentlessly push the boundaries of knowledge, we are deliberately venturing into a domain where those familiar classical rules gracefully yield to the counterintuitive, probabilistic, and deeply interconnected laws of the quantum realm. This demands an entirely different approach to engineering, requiring new ways of thinking, novel tool sets, and fostering a new generation of scientific and engineering talent. The very concept of quantum entanglement, once a source of profound philosophical unease, is now universally recognized as an extraordinarily potent resource, a fundamental building block for technologies that until recently belonged purely to the realm of science fiction. The unparalleled ability to generate, meticulously manipulate, and preserve these delicate, non-local connections between particles allows us to encode and process information in ways fundamentally distinct from anything classical. This isn't merely about developing faster transistors. It's about pioneering entirely new computational architectures, designing novel communication protocols, and forging new methods of interacting with the physical world that draw directly from the universe's deepest, most counterintuitive principles. We currently find ourselves in the nascent stages of this quantum age, a period remarkably analogous to the very beginnings of classical computing in the mid-20th century. The quantum computers we possess today are nascent, often demanding specialized ultra-cold environments, and are still susceptible to errors. The quantum networks in existence remain prototypes spanning relatively constrained distances. Yet the breathtaking pace of progress in laboratories worldwide is nothing short of astounding. Breakthroughs in qubit stability, error correction techniques, and entanglement distribution are occurring at an accelerating rate, propelled by a global imperative to unlock the full transformative potential of these technologies. This burgeoning technological frontier promises to reshape our world in ways both profound and currently unforeseen. Its impact will reverberate across industries from global finance and healthcare to national defense and renewable energy. It will enable scientific discoveries that are presently beyond our wildest imaginings, allowing us to meticulously simulate complex biological processes, design materials with atomic-level precision, and perhaps even unravel the universe's most fundamental mysteries with unprecedented clarity. The journey to fully realize the quantum age will undoubtedly be long and challenging, but the destination, a world fundamentally transformed by the intrinsic power of entanglement, is a future brimming with immense possibility and wonder. We are undeniably standing at the precipice of a quantum revolution. Quantum entanglement, now unequivocally confirmed as a fundamental truth of our universe through decades of painstaking experimentation, might still evoke a visceral reaction. Albert Einstein's iconic dismissal of spooky action at a distance continues to resonate, capturing the intuitive struggle many of us feel when confronting this bizarre quantum reality. Even for seasoned physicists, this phenomenon retains an intrinsic sense of wonder, directly confronting our deeply ingrained classical expectations for how the cosmos ought to operate. This enduring spookiness does not stem from any lingering uncertainty regarding entanglement's precise mathematical description or its robust empirical verification. We possess accurate equations to model its behavior, and we can reliably generate and measure entangled particles. Rather, the profound disquiet originates from entanglement's stark defiance of our everyday macroscopic experience. Our minds have evolved to comprehend a universe governed by local realism, where objects possess definitive properties, irrespective of observation and influences, traverse space at finite measurable speeds. Entanglement, with its instantaneous non-local correlations, directly challenges both these fundamental intuitive precepts. In our familiar world, a flipped coin is either definitively heads or tails. A thrown ball follows a singular predictable trajectory. A message dispatched requires a finite duration to reach its recipient. These are the ingrained rules our macroscopic minds have internalized. Yet within the quantum domain, entangled particles function as a single indivisible system, their properties instantaneously linked across immense distances. Information as we understand it is not sent. Rather, their shared quantum state persists, as if they were never truly distinct entities. This bewildering unity fundamentally questions our notions of individuality and physical separation, hinting at a profound underlying fabric of reality that remains exceedingly challenging, if not impossible, to concretely visualize in classical terms. So yes, in a very real sense, entanglement is still spooky. This quality arises not from its being unproven or mystical, but from its profound revelation of a reality that operates according to principles utterly alien to our common-sense experience. It serves as a constant, powerful reminder that our intuitive grasp of the universe, while remarkably effective for daily life, represents an incomplete canvas when we peer into its most fundamental building blocks. This enduring sense of wonder, coupled with its intellectual challenge, is precisely what renders entanglement such a captivating subject. It continually inspires novel theoretical interpretations and propels further experimental explorations, compelling us to expand our mental frameworks and embrace a cosmos that is infinitely richer and more profoundly unified than we had ever conceived. The rigorous experimental verification of quantum entanglement has decisively settled the fundamental debate over local realism, confirming that the universe is indeed far stranger and more interconnected than our classical intuitions once allowed. Yet proving entanglement's existence is merely the first step. Fully comprehending its ultimate nature and its profound place within the cosmic tapestry is an entirely different frontier. Despite the monumental breakthroughs, entanglement continues to harbor deep mysteries, sparking a new generation of fundamental, unanswered questions that relentlessly drive active research at the cutting edge of theoretical physics. One of the most pressing inquiries centers on entanglement's intimate connection to gravity and the very fabric of space-time. Our two most triumphantly successful theories of the universe, quantum mechanics, which exquisitely describes the subatomic realm and its fundamental forces, and general relativity, which elegantly describes gravity and the cosmos on vast scales, remain fundamentally incompatible. Entanglement, with its non-local instantaneous correlations, appears to transcend spacetime in a way that directly challenges general relativity's smooth, continuous fabric. Some bold speculative theories propose that entanglement might actually give rise to spacetime itself, or that wormholes' hypothetical tunnels through spacetime could be the macroscopic manifestation of entangled black holes. Exploring these profound connections is absolutely crucial for developing a unified theory of quantum gravity, a long-sought theory of everything that can finally reconcile these two pillars of modern physics. Another area of intense investigation concerns the precise mechanism of wave function collapse. While we consistently observe that superposition resolves into a definite state upon measurement, the exact what and when of this process remain elusive. Does consciousness play a role? Is it merely interaction with a classical environment, a process called decoherence, that causes the collapse? Or is it a fundamental inherent process of the universe, perhaps governed by a new, yet-to-be-discovered law of physics? A deeper understanding of collapse is essential for transitioning quantum technologies from fragile laboratory setups to robust real-world applications, as it dictates how long delicate quantum states can be maintained before losing their special properties. Furthermore, physicists are continually exploring the limits of entanglement. Can absolutely anything become entangled? We have successfully entangled photons, electrons, and even small molecules. But can truly macroscopic objects, billions of atoms strong, also exhibit entanglement? While theoretical predictions suggest yes, the pervasive nature of decoherence makes it extraordinarily difficult to observe such states. Experiments are relentlessly pushing the boundaries, attempting to entangle progressively larger and more complex systems, striving towards the elusive boundary where the quantum world seamlessly transitions into the classical world. Pinpointing this precise transition point could offer profound insights into the very nature of reality itself. Then there is the overarching question of what entanglement is beyond being a mere correlation. Is it a form of information, a fundamental physical resource, a deeper geometric property of spacetime itself? Different interpretations of quantum mechanics, from the well-established Copenhagen interpretation to the intriguing many-worlds theory or various objective collapse theories, offer divergent philosophical frameworks for what entanglement means for reality. While experiments have definitively proven entanglement's existence, they have not yet unequivocally revealed which interpretation provides the most complete and accurate picture of the underlying reality. These profound, persistent, unanswered questions vividly illustrate that while we have made monumental strides in understanding quantum entanglement, our thrilling journey into the quantum realm is far from complete. Entanglement remains a source of endless fascination and an incredibly powerful driver for cutting-edge scientific exploration. It continues to challenge our most fundamental assumptions, inspiring physicists worldwide to probe deeper into the intrinsic nature of reality, constantly pushing the very boundaries of human knowledge and reminding us that the universe holds secrets far more intricate, astonishing, and compelling than we can currently comprehend. The irrefutable experimental evidence for quantum entanglement has profoundly reshaped our understanding of the universe. Its once bizarre nature is no longer a mere theoretical curiosity or a subject of philosophical debate. It is an undeniable empirical fact. But while the experiments have delivered a clear verdict on what the universe, does they compel us to confront an even deeper, more fundamental question? What does this mean for the very nature of reality itself? Quantum entanglement, more than any other phenomenon, continually pushes the boundaries of philosophical thought, forcing us to fundamentally re-evaluate concepts as foundational as local realism, determinism, and the very role of observation within the cosmos. For centuries, the bedrock of scientific understanding rested upon a worldview that felt inherently intuitive. Local realism. This two-pronged concept posited that objects possess definite intrinsic properties, regardless of whether they are observed realism, and that any influence between objects must travel through space at a finite speed, never exceeding the speed of light locality. Our classical physics, from Newton's celestial mechanics to Einstein's theory of relativity, flourished within this framework, painting a picture of a predictable objective universe. The moon, so the argument maintained, existed with its definitive shape and position, even when no one was looking. Its attributes were fixed independent of any observer. And a cause here could only produce an effect there if some signal propagating through space bridged the intervening gap. However, entanglement utterly shatters this comforting classical edifice. The decisive Bell tests, through their unequivocal violation of Bell's inequalities, have demonstrated that at least one of these two foundational pillars, realism or locality, must be false. The correlations meticulously observed between entangled particles are simply too strong, too instantaneous to be accounted for by any pre-existing local properties. This implies that particles truly do not possess definite properties until they are measured directly challenging realism. Furthermore, the immediate non-local connection between them defies our understanding of localized influences, striking at the heart of locality. The universe, at its most fundamental level, is fundamentally non-local. It is a profoundly interconnected reality where particles remain intertwined in ways that transcend spatial separation. This revelation forces a radical reorientation of our intuitive grasp of existence. This profound re-evaluation extends directly to the concept of determinism. In a classically deterministic universe, every event is theoretically predetermined by prior causes. Given sufficient information about initial conditions, one could in principle predict the future with absolute certainty. The quantum realm, however, introduces an inherent, irreducible randomness. As we observed with superposition, a particle exists as a blur of possibilities, until measured. The outcome of that measurement is fundamentally probabilistic, not deterministic. While we can predict the likelihood of an outcome, we cannot predict the specific outcome of a single quantum event. Entanglement amplifies this. The perfectly correlated outcomes between distant entangled particles are for each individual measurement fundamentally random. This means that the universe at its most granular level might not be a perfectly predictable clockwork mechanism. Instead, it may incorporate a fundamental element of genuine chance intricately woven into its very fabric. This challenges millennia of philosophical and theological thought concerning free will and the nature of predestination. If the universe truly does play dice, as Einstein famously feared, then our understanding of cause-effect and the very unfolding of reality must undergo a radical paradigm shift. Perhaps the most philosophically challenging aspect of entanglement, and indeed of quantum mechanics as a whole, is the enigmatic role of observation, or measurement. Schrödinger's cat vividly illuminated the measurement problem. When and how does a quantum superposition, such as a cat being simultaneously alive and dead, transition into a single definite reality? Different interpretations of quantum mechanics grapple with this profound question, each offering a distinct philosophical lens through which to view the universe. The Copenhagen interpretation, famously championed by Niels Bohr, asserts that reality only becomes definite upon measurement. Prior to measurement, quantum systems exist as probabilities. The act of observation or interaction with a classical measuring apparatus is what actively forces the wave function to collapse, actualizing one of the possibilities. This implies that the observer is not a detached entity, but an integral participant in shaping reality. But what precisely constitutes an observer? Is it a conscious mind, or merely any irreversible interaction that amplifies a quantum event to a classical scale? This interpretation suggests a reality fundamentally tied to our interaction with it, a notion deeply unsettling to those who champion an objective universe independent of human perception. Other interpretations offer compelling alternative perspectives. The Bebot, many worlds interpretation, for instance, entirely bypasses the concept of wave function collapse. Instead, it posits that every time a quantum measurement is made, the universe itself branches into multiple parallel realities, one for each possible outcome. In the case of Schrödinger's cat, upon opening the box, the universe doesn't choose between a live or dead cat. Rather, the universe splits into two distinct branches, one where the cat is alive, and the observer experiences that outcome, and another where the cat is dead, and a copy of the observer experiences that outcome. In this view, all possibilities are realized in some parallel universe, and our individual perception is simply our experience of one particular branch. While MWI elegantly resolves the measurement problem by removing collapse, it introduces an unfathomable multiplicity of universes, a concept equally challenging to our intuition. Then there are objective collapse theories, which propose that wave function collapse is a spontaneous physical process that occurs independently of any observer, perhaps triggered by exceeding a certain mass energy or complexity threshold. These theories suggest the existence of new, yet-to-be-discovered physics at the intersection of the quantum and classical worlds, where quantum superpositions automatically decohere and collapse without the explicit need for an external measurement. This would potentially restore a sense of objectivity to reality, but at the cost of introducing new fundamental laws of nature. These diverse interpretations are not just academic curiosities. They represent humanity's ongoing profound struggle to make sense of a universe that stubbornly refuses to conform to our ingrained classical expectations. Entanglement, by forcing the issues of non-locality and the measurement problem into stark relief, pushes these philosophical discussions to the very forefront of scientific inquiry. It compels us to rigorously re-examine the very definition of reality. Is it something inherently existing out there, entirely independent of us? Or is it something subtly constructed or even co-created through our interaction with its fundamental components? The undeniable truth of entanglement reveals a universe that is both more deeply unified and potentially more profoundly fragmented than we ever imagined. Unified because distant particles are inextricably linked by a shared quantum destiny. Fragmented because their individual realities remain indefinite until observed, potentially leading to multiple outcomes or even branching universes. It blurs the conventional lines between subjective perception and objective reality, prompting profound questions about consciousness, information, and the deep, mysterious connections that bind every particle in the cosmos. This intellectual journey is far from over as entanglement continues to serve as our most powerful lens into the deepest, most counterintuitive truths about existence. Our journey through the quantum realm has been one of extraordinary revelations. We began by grappling with the baffling paradox of quantum entanglement, a phenomenon that seemed to defy our most cherished classical intuitions about reality. Together, we navigated the intricate concepts of wave-particle duality, fundamental uncertainty, and the astonishing power of superposition. We then delved into the epic intellectual clash between Einstein's steadfast belief in local realism and Bohr's unwavering acceptance of quantum strangeness. Finally, we witnessed the meticulous experimental triumphs that definitively settled the debate, proving beyond any reasonable doubt that entanglement is an undeniable intrinsic truth of our universe. This triumphant confirmation of entanglement, however, marks not a culmination, but merely a glorious new chapter in humanity's ceaseless voyage of scientific discovery. The very essence of science is a perpetual exploration, a tireless pursuit of knowledge, where every answer found invariably illuminates a fresh, deeper set of questions. Entanglement stands as a powerful testament to this ongoing process, showcasing humanity's insatiable curiosity and our remarkable capacity to illuminate the universe's most elusive truths. For millennia, human civilization has tirelessly striven to comprehend the cosmos, driven by a primal urge to make sense of our existence. From charting distant constellations to deciphering the atom's innermost workings, each epoch-defining discovery has profoundly reshaped our worldview, compelling us to set aside old certainties and embrace new, often counterintuitive realities. The quantum revolution, with entanglement at its very core, is perhaps the most dramatic illustration of this continuous evolution of understanding. It has revealed that reality at its most fundamental level is far more intricate, interconnected, and surprising than our macroscopic experiences could ever have suggested. The intellectual struggle over entanglement spanning generations of brilliant minds perfectly embodies this relentless scientific spirit. Its resolution was not dictated by dogma or philosophical decree, but by rigorous experimentation, by scientists pushing the boundaries of precision and ingenuity to their very limits. This unwavering commitment to empirical verification, this courageous willingness to challenge deeply ingrained beliefs in the face of compelling evidence, is the hallmark of true scientific progress. It serves as a potent reminder that our comprehension of the universe is never truly complete. It is a dynamic, ever-unfolding tapestry woven from observation, theoretical insight, and relentless questioning. Even with entanglement definitively proven and its technological applications beginning to emerge, the phenomenon itself continues to spark new, profound inquiries. How does entanglement genuinely relate to gravity and the very structure of space-time? What is the precise mechanism by which a quantum superposition resolves into a definite state? And exactly where does the quantum world seamlessly merge into the classical? Can we engineer and sustain entanglement in increasingly macroscopic objects, truly pushing the limits of this peculiar connectedness? These are not trivial details. They are fundamental questions that beckon the next generation of physicists to delve deeper, to conceptualize revolutionary new theories, and to design even more sophisticated experiments that interrogate the universe at its absolute foundations. Entanglement thus serves as a constant humbling reminder that the universe holds secrets far grander and more astonishing than we can currently grasp. It fuels our intellectual hunger, stretching the very boundaries of human thought and imagination. The quest to fully understand the cosmos is an infinite expedition, a continuous unveiling of deeper layers of reality. And in this endless pursuit, entanglement stands as a brilliant beacon, illuminating the path forward, profoundly demonstrating our capacity not only to marvel at the universe's wonders, but to actively participate in uncovering its most astonishing truths. Our extraordinary journey through the quantum realm culminates now having unveiled one of the universe's most profound and once baffling secrets: quantum entanglement. We began by confronting a phenomenon that defied our deepest classical intuitions, where particles seemed to reach across unimaginable distances with instantaneous effect. We navigated the perplexing landscapes of wave-particle duality, intrinsic uncertainty, and the astonishing power of superposition. Then we witnessed the titanic intellectual clash between Albert Einstein's yearning for a locally real, deterministic universe and Niels Bohr's courageous embrace of quantum weirdness. And ultimately, we bore witness to the meticulous, unwavering experimental triumphs that for decades rigorously proved beyond any credible doubt that entanglement is an undeniable fundamental truth of our cosmos. This profound validation of quantum entanglement carries immense implications, irrevocably reshaping not only our fundamental understanding of the universe, but also heralding a new era of technological advancement. For centuries, our perception of reality was anchored in the comforting tenets of classical physics: a world of distinct objects, local causes, and predictable outcomes. Entanglement has shattered this intuitive picture. It compels us to accept that at its most fundamental level, the universe is inherently non-local, a place where particles exist not as separate entities, but as intrinsically linked components of a grand unified system, their fates instantaneously intertwined, regardless of spatial separation. We must now acknowledge an inherent fundamental randomness, a cosmic roll of the dice woven into the very fabric of existence, challenging millennia of deterministic thought. And most strikingly, it elevates the role of observation and measurement into a central active position, suggesting that reality itself might be far more participatory than we ever conceived. These are more than mere scientific revelations. They are philosophical transformations demanding that we redefine our most basic assumptions about what is real, individual, and knowable. Yet entanglement transcends mere philosophical re-evaluation. It is a potent new resource poised to ignite a technological revolution unlike any before it. The very principles that once caused Einstein such profound discomfort are now being meticulously engineered into groundbreaking tools that promise to redefine our capabilities across every critical domain. We stand at the very threshold of a quantum age where the impossible is swiftly becoming the imminent. Consider the staggering potential of quantum computing. By harnessing superposition and entanglement, these nascent machines promise to solve problems utterly intractable for even the most powerful classical supercomputers. Imagine accelerating the discovery of life-saving drugs by simulating molecular interactions with unprecedented accuracy, or engineering novel materials with atomic precision for energy transportation and manufacturing. Picture breakthroughs in artificial intelligence, navigating complex datasets to unlock insights currently beyond reach, or optimizing global logistics and financial models with unparalleled efficiency. This is not simply faster computation. It is a fundamental redefinition of what is computationally feasible. Then there is the promise of unconditionally secure communication. Quantum cryptography powered by entanglement and the no-cloning theorem offers a level of security guaranteed by the immutable laws of physics. Any attempt to eavesdrop inherently disturbs the quantum state, leaving an undeniable footprint that alerts the communicating parties. This is the future of truly private communication, safeguarding our most sensitive data against any future technological advancement, even the advent of quantum computers themselves. Beyond these, the grand vision of a quantum internet beckons a global network connecting quantum processors with entanglement, enabling distributed quantum computing and ultra-secure global communication on an unprecedented scale. We also glimpse the transformative power of entanglement in quantum sensing and metrology. Pushing the limits of measurement precision for everything from atomic clocks that will redefine global timing to ultra-sensitive magnetic field sensors for medical diagnostics and geological surveys. Advanced quantum imaging promises to visualize the microscopic world with unprecedented clarity and minimal invasiveness, opening new windows into biology and materials science. The journey to fully harness these capabilities will undoubtedly be long and challenging, fraught with engineering hurdles and the constant demand for new scientific insights. Today's quantum computers are still in their infancy, delicate and error-prone. Building scalable quantum networks requires overcoming immense technical obstacles to maintain quantum coherence over vast distances. Yet the relentless pace of progress in laboratories worldwide, driven by global collaboration and ingenuity, is nothing short of breathtaking. Breakthroughs are occurring at an accelerating rate, fueling an optimistic and audacious vision for the future. The quest to comprehend the quantum realm, indelibly marked by the perplexing dance of entanglement, stands as an enduring testament to humanity's relentless pursuit of knowledge. It is a constant reminder that the universe is far more intricate, more interconnected, and more fundamentally astonishing than our everyday senses can grasp. It challenges our deepest assumptions, ignites our imagination, and inspires us to continue pushing the very boundaries of what is known. As we peer into the coming decades, one truth shines with unwavering clarity. The future is quantum. And in that future, the bizarre, beautiful, and profoundly useful phenomenon of quantum entanglement will play a central transformative role, continuing to unveil the deepest secrets of reality and empowering humanity with capabilities once considered pure fantasy. The spooky action of entanglement has unveiled a universe where reality is more interconnected, astonishing, and profoundly powerful than we ever dared to imagine. If you're eager to continue exploring the astonishing interconnectedness of our universe, subscribe to join us on our next scientific adventure. Don't forget to subscribe to Astro Horizons and hit the notification bell.